Hello there, and welcome to Space Historians. I'm so glad you found your way here tonight. Before we begin, take a moment to get comfortable. Let your body settle wherever you are. There's no rush. We have all the time we need. Where in the world are you watching from? A quiet bedroom as the night deepens? Perhaps a cozy corner where the day is finally winding down? Wherever you are, you're exactly where you need to be. Tonight we're going to explore one of the most extreme and mysterious objects in the entire universe, Magnetars. These are neutron stars with magnetic fields so powerful they defy comprehension. Objects so dense that a teaspoon of their matter would weigh as much as a mountain. Spinning objects that can release more energy in a tenth of a second than our sun does in 1,000 years. We'll discover how these cosmic titans are born from the violent deaths of massive stars, understand the physics that makes them possible, and contemplate what they tell us about the extremes of nature. But don't worry, this isn't going to be an anxiety-inducing journey into cosmic violence or existential terror. Instead, we'll move slowly and carefully through these remarkable objects, learning about their properties, their behaviour, and their place in the cosmic story. By the end, I think you'll find a deep appreciation for just how strange and wonderful the universe can be, and perhaps a peaceful acceptance that nature operates at scales far beyond our everyday experience. If you enjoy these calm explorations of cosmic mysteries, a like and subscribe really helps reach others seeking the same peaceful way to end their day, and to those already subscribed. Thank you for being part of this community of curious minds, so settle in. Let your shoulders drop, take a slow breath, and let it out even more slowly. And let's begin our slow drift through the realm of Magnetars, the universe's most powerful magnets. There's nowhere you need to be, just listen and let the story unfold. Let your thoughts wander among the stars and know that sleep will come when it's ready. Let's start with the question itself, because understanding what a magnetar is requires us to think about matter and energy in ways that challenge our everyday intuitions. A magnetar is a type of neutron star, but not just any neutron star. It's a neutron star with a magnetic field thousands of times stronger than typical neutron stars, and neutron stars already have the strongest magnetic fields of any normal astronomical objects. To give you a sense of scale, a refrigerator magnet has a magnetic field of about 100 Gauss. The Earth's magnetic field, which protects us from solar radiation and makes compasses work, is about half a Gauss at the surface. A strong laboratory magnet might reach 10,000 Gauss. An ordinary neutron star has a magnetic field of about 1 trillion Gauss, already mind-boggling compared to anything on Earth. A magnetar has a magnetic field of 1 quadrillion Gauss or more. That's 1,000 trillion, written as 1 followed by 15 zeros. At this strength, the magnetic field does things that seem impossible. It warps the electron clouds around atoms, making matter itself behave differently. It can rip atoms apart at a distance. It affects the vacuum of space itself, making light behave strangely. If a magnetar existed halfway between Earth and the Moon, about 200,000 kilometers away, its magnetic field would be strong enough to erase every credit card, hard drive and magnetic storage device on the planet. It would disrupt our bodies at the cellular level, affecting the ions that our nerves use to send signals. From that distance, it could be lethal. But magnetars don't exist anywhere near Earth, thankfully. They're out in deep space, typically thousands of light years away, remnants of massive stars that died in spectacular supernova explosions. We know of only about 30 confirmed magnetars in our galaxy, out of perhaps 1 billion neutron stars total. They're rare, exotic, extreme in every way we can measure. A magnetar is also incredibly small for something so powerful. Despite containing more mass than our Sun, a magnetar is only about 20 kilometers across. That's roughly the size of a city. Manhattan is longer than a magnetar is wide, yet into that tiny volume is compressed 1.4 times the mass of the Sun, maybe more. The density is so extreme that matter is crushed into a state that exists nowhere else in the universe except in neutron stars and perhaps in the cores of black holes. Imagine taking all the people on Earth, all 7 billion of us, and compressing us down to the size of a sugar cube. That gives you a rough sense of neutron star density. Every cubic centimetre, about the size of a sugar cube, contains hundreds of millions of tons of matter. A teaspoon of neutron star material would weigh about 5 billion tons on Earth, as much as Mount Everest. And magnetars spin. Not slowly like the Earth, which takes 24 hours to rotate once but rapidly, completing one full rotation in anywhere from 2 to 12 seconds. Some spin even faster. This rotation, combined with the extreme magnetic field, creates a cosmic lighthouse effect, where beams of radiation sweep across space as the magnetar spins. The radiation isn't gentle. Magnetars emit X-rays and gamma rays, the most energetic forms of light in the universe. Sometimes they flare, releasing enormous bursts of energy in fractions of a second. The largest magnetar flare ever observed, from a magnetar called SGR 1806-20, released more energy in 1/10 of a second than the sun emits in 100,000 years. That's the kind of power we're talking about. But despite this violence, despite these extremes, magnetars are in some sense very simple objects. They're made almost entirely of neutrons, the neutral particles found in atomic nuclei. They have a thin crust of more familiar matter, mostly iron nuclei arranged in a crystal lattice, but beneath that is a sea of neutrons, packed so tightly they flow like a superfluid, a quantum liquid with zero viscosity. Understanding magnetars means understanding matter at its most extreme, magnetic fields at their strongest, gravity at its most intense. It means thinking about physics in regimes we can never recreate on Earth, where all our intuitions fail and only mathematics can guide us. But we can still approach these objects gently, with curiosity rather than fear, appreciating them as natural wonders, as extreme laboratories where the universe shows us what's possible. To understand where magnetars come from, we need to talk about the deaths of stars. Not just any stars, but massive stars, the giants and supergiants that burn brilliantly but briefly, living only millions of years compared to the sun's 10 billion year lifespan. Stars are born from clouds of gas and dust in space. Gravity pulls the material together, and as the cloud collapses, it heats up. Eventually, the centre becomes hot and dense enough for nuclear fusion to begin. Hydrogen atoms fuse into helium, releasing energy in the process. This energy creates an outward pressure that balances the inward pull of gravity. The star reaches equilibrium and settles into a long, stable life. For stars like our Sun, this equilibrium lasts billions of years. But for massive stars, stars with 10, 20, 50 times the Sun's mass, the story is different. These stars burn through their fuel much faster because their cores are hotter and denser. Fusion happens more rapidly. They shine more brightly, but they die much younger. When a massive star exhausts the hydrogen in its core, it doesn't simply fade away like smaller stars do. Instead, it begins fusing helium into carbon and oxygen. Then it fuses those into heavier elements, neon, magnesium, silicon, sulfur, all the way up to iron. Each stage happens faster than the last. The star develops an onion-like structure, with different layers fusing different elements. But iron is the end of the line. Fusing iron doesn't release energy, it consumes energy. When the core turns to iron, there's no more fuel left. The outward pressure from fusion stops. Gravity wins. What happens next occurs incredibly fast. The iron core, roughly the size of Earth but containing more mass than the Sun, collapses. In less than a second, it shrinks from thousands of kilometres across to just 20 or 30 kilometres. The protons and electrons in the iron nuclei are crushed together, forming neutrons and releasing neutrinos. The collapse is so sudden, so violent, that it triggers a shockwave that blows the rest of the star apart in a supernova explosion. For a brief moment, the supernova outshines an entire galaxy. The explosion scatters the star's outer layers into space, seeding the cosmos with heavy elements that will eventually form new stars, planets, and perhaps life. But the core remains, crushed to incredible density, now a neutron star. Most neutron stars are born with strong magnetic fields, inherited and amplified from the original star's magnetic field during the collapse. The conservation of magnetic flux means that as the star shrinks, its magnetic field intensifies. It's like a figure skater pulling in their arms to spin faster, except instead of angular momentum. We're talking about magnetic flux, but magnetars are different. Their magnetic fields are about 1,000 times stronger than ordinary neutron stars. Scientists think this extra boost might come from a dynamo effect during the first few seconds after the neutron star forms. If the newborn neutron star is spinning very rapidly, and if it's hot and turbulent inside, convection currents in the superfluid neutron matter might generate enormous magnetic fields, amplifying them beyond what would come from simple compression alone. Another possibility is that magnetars are born from particularly massive progenitor stars that had very strong magnetic fields to begin with. Or perhaps the collapse happens in a special way, with the core spinning especially fast or with particular internal dynamics that favour strong field generation. The truth is, we're not entirely sure. The conditions inside a collapsing stellar core are so extreme that our models struggle to capture all the physics. What we do know is that magnetars are born in these catastrophic stellar deaths, emerging from the chaos with magnetic fields powerful enough to dominate their entire existence. The magnetic field stores enormous energy, and over time, as the magnetar ages, that energy is gradually released through radiation, through flares, through the slow decay of the field itself. Young magnetars are probably the most active, the most violent, releasing the most energy. As they age over thousands to millions of years, they gradually cool and calm down, their magnetic fields weakening, their rotation slowing. Eventually they might fade into quieter objects, no longer emitting detectable radiation, becoming the cosmic ghosts of once brilliant magnetic titans. But in their youth, in their first thousands of years, magnetars are among the most energetic objects in the universe, shining in X-rays, occasionally flaring with the power of 1,000 suns, reminders that stellar death can create objects as strange and extreme as the deaths themselves are violent. Let's think about what a magnetic field actually is, and why the magnetic fields of magnetars are so extraordinary. This will help us understand what makes these objects unique, and why they behave the way they do. A magnetic field is a region of space where magnetic forces can be felt. It's created by moving electric charges, by electric currents. In an ordinary magnet, the magnetic field comes from the alignment of electrons spinning in atoms. In Earth's core, the magnetic field comes from convection currents in the molten iron. In a magnetar, the magnetic field comes from the motion of charged particles in the neutron star's crust, and possibly from currents in the superfluid interior. Magnetic fields have strength and direction. We measure their strength in units called Gauss or Tesla. 1 Tesla equals 10,000 Gauss. The fields we encounter in everyday life are typically fractions of a Gauss to maybe a few thousand Gauss in strong laboratory magnets. In these ordinary magnetic fields, the effects are straightforward. Magnetic fields exert forces on moving charges and on other magnets. They can attract iron, deflect compass needles, focus beams of charged particles. But at higher strengths, magnetic fields begin to do stranger things. At about 10 million Gauss, magnetic fields start to affect the structure of atoms. The electron orbitals, normally spherical or dumbbell-shaped, get stretched into elongated shapes. Atoms become polarized, their properties changing depending on their orientation relative to the field. Chemistry starts to work differently. At 1 billion Gauss, atoms can no longer maintain their normal structure. The magnetic forces become comparable to the electric forces holding atoms together. Matter transitions to a strange state where electrons move in highly quantized orbits, forming what are called Landau levels. The material becomes highly anisotropic. behaving differently in different directions. At a trillion Gauss, the typical field strength of ordinary neutron stars, the effects are even more dramatic. The vacuum of space itself is affected. Quantum electrodynamics, the theory describing how light and matter interact, predicts that in strong magnetic fields, the vacuum can become birefringent, meaning it affects light differently depending on the light's polarization. Empty space acts like a crystal, splitting light beams. And at a quadrillion Gauss, the realm of Magnetars, physics enters truly exotic territory. The magnetic field energy density becomes enormous, comparable to the energy density of matter itself. The field can store so much energy that its pressure affects the structure of the neutron star. The star isn't just held together by gravity and neutron degeneracy pressure. The magnetic field contributes to the force balance. In such strong fields, virtual particles that normally pop in and out of existence in the quantum vacuum can be affected by the field, changing their behaviour. Photons, particles of light, can split into multiple photons, or convert into electron-positron pairs, then convert back. The vacuum becomes an active medium. Not just empty space. These extreme magnetic fields also create tremendous stresses in the neutron star's crust. The crust is made of iron nuclei arranged in a crystal lattice, immersed in a sea of electrons. The magnetic forces twist and strain this crust. Over time, the stresses build up until the crust fractures, like an earthquake on Earth but far more violent. When the crust fractures, it's called a starquake. The magnetic field lines anchored in the crust suddenly snap to a new configuration. This releases enormous amounts of energy in a fraction of a second, creating what we observe as a Magnetar flare or burst. The energy comes out as X-rays and gamma rays, and sometimes as a pulse of lower frequency radiation that can be detected across the electromagnetic spectrum. The largest flares release 10 to the 46 ergs of energy in a tenth of a second. To put that in perspective, the Sun's total energy output is about 4 times 10 to the 33 ergs per second. So a Magnetar flare can release in a fraction of a second what the Sun emits in more than 100,000 years. It's hard to grasp that kind of power, but the magnetic field doesn't just cause starquakes, it also affects the star's rotation. As the Magnetar spins, its magnetic field lines extend into space, filled with charged particles. These particles radiate energy, and that radiation carries away angular momentum, slowing the star's spin. This is called magnetic braking. For magnetars, magnetic braking is especially strong because the magnetic fields are so intense. Young magnetars spin rapidly, maybe once per second or faster. Over thousands of years, they slow down to once every few seconds or even longer. The spin-down rate depends on the magnetic field strength, so by measuring how fast a magnetar is slowing, we can estimate its magnetic field. This connection between magnetic field, rotation, and age gives us a way to study magnetar evolution. We can estimate how old a magnetar is by looking at its spin period and how fast it's slowing down. We can track how the magnetic field evolves over time. We can see the gradual transition from young active magnetar to old, quiet neutron star. The physics of extreme magnetism is still not fully understood. We can't create such fields in laboratories, so we can't test all our theories directly. Instead, we rely on observations of magnetars and other neutron stars, combined with theoretical calculations and simulations. Each new observation refines our understanding, revealing more about how matter and energy behave in these extreme conditions. The story of magnetar discovery is a tale of unexpected observations, puzzling data, and the gradual realization that the universe contains objects even stranger than scientists had imagined. Let's trace that journey, because it shows how science works, how we come to understand new phenomena. Neutron stars were predicted theoretically in the 1930s, shortly after the discovery of the neutron itself. Physicists realized that if a star's core collapsed, the protons and electrons could merge to form neutrons, creating an incredibly dense object. But it was just a theory, an interesting possibility. No one had observed such a thing. That changed in 1967 when Jocelyn Bell Burnell, a graduate student working with Anthony Hewish at Cambridge, discovered pulsars. She noticed a strange, regular radio signal, pulsing once every 1.3 seconds. At first, she and her colleagues jokingly called it LGM-1, for wondering if it might be an artificial signal from an alien civilization. But soon they found more pulsars, and the explanation became clear. These were rapidly spinning neutron stars, emitting beams of radio waves from their magnetic poles. As the star rotated, the beams swept across Earth like a lighthouse, creating the pulsing signal. The discovery confirmed that neutron stars really existed and opened up a new field of astronomy. Over the following decades, astronomers discovered many pulsars, most of them spinning rapidly, emitting radio waves, gradually slowing down as they aged. The picture seemed clear. Neutron stars were born in supernova explosions, initially spinning very fast, and over millions of years they slowed down and faded. But in 1979, something unexpected happened. Satellites designed to detect gamma-ray bursts from Soviet nuclear tests picked up a strange signal from space. On March 5th, a pulse of gamma rays hit several spacecraft simultaneously. The pulse lasted about 1/5 of a second and was incredibly bright, saturating the detectors. The source was traced to a region in the Large Magellanic Cloud, a small galaxy orbiting our Milky Way, about 160,000 light-years away. The object was designated SGR 0526-66, where SGR stands for Soft Gamma Repeater. Over the following years, it emitted more bursts, irregular pulses of soft gamma rays and X-rays. Similar objects were discovered, forming a small class of soft gamma repeaters and a related class called anomalous X-ray pulsars. These objects emitted X-rays more intensely than could be explained by their rotation alone. They spun relatively slowly, with periods of several seconds, and they didn't fit the standard pulsar model. The puzzle deepened. If these objects were powered by rotational energy like ordinary pulsars, they shouldn't be emitting so much energy. Their spin down wasn't fast enough. There had to be another energy source. But what? In 1992, two scientists, Robert Duncan and Christopher Thompson, proposed a radical idea. What if these objects had magnetic fields far stronger than ordinary neutron stars? What if the energy source wasn't rotation but the gradual decay of an ultra-strong magnetic field? They called these hypothetical objects magnetars. The idea was initially met with skepticism. Magnetic fields that strong seemed extreme, even by neutron star standards. But as more observations came in, the Magnetar model started to make sense. The X-ray emission, the irregular bursts, the slow spin periods, all could be explained if these objects had magnetic fields of a quadrillion Gauss or more. The key evidence came from measuring the spin-down rates. By carefully timing the pulses from these objects over years, astronomers could see how fast they were slowing. The spin-down was too rapid to be explained by ordinary magnetic braking with normal neutron star fields. But if the magnetic field was 1,000 times stronger, the numbers worked out. In 1998, strong evidence came from an object called SGR 1900-14. Astronomers detected a glitch, a sudden change in the object's rotation rate, suggesting a starquake had occurred. This supported the idea that magnetars have highly stressed crusts that occasionally fracture. Then in December 2004 came the most spectacular magnetar event ever observed. SGR 1806-20, a magnetar about 50,000 light-years away, emitted a giant flare. The initial spike of gamma rays was so bright it saturated every satellite that detected it. The flare lasted about 1/10 of a second, followed by a pulsating tail lasting several minutes. The energy release was staggering. Even though the flare happened 50,000 light-years away, it affected Earth's ionosphere, the upper atmosphere where ions and electrons reside. The burst of gamma rays ionized atoms in the ionosphere, causing detectable changes in radio wave propagation. It was the first time an event from outside our solar system had a measurable impact on Earth's atmosphere. This giant flare confirmed the Magnetar model beyond doubt. Only an ultra-strong magnetic field undergoing a catastrophic reconfiguration could release that much energy so quickly. Since then, about 30 Magnetars have been confirmed, with perhaps more awaiting discovery. Each one provides a new laboratory for studying extreme physics. The discovery of Magnetars reminds us that the universe is full of surprises, that nature is more creative and extreme than our imaginations. It also shows the power of patient observation and theoretical thinking. The objects were there all along, emitting their strange signals, waiting for us to build the right instruments and develop the right ideas to understand them. Let's explore what a magnetar actually looks like inside, because understanding its structure helps us appreciate just how strange and extreme these objects are. We'll move from the surface down to the core, layer by layer, discovering the exotic states of matter that exist in conditions we can never recreate on Earth. At the surface, a magnetar has an atmosphere, though it's nothing like Earth's atmosphere. The temperature is about 1 million degrees Kelvin, hot enough to vaporize any ordinary matter. The atmosphere is incredibly thin, perhaps only a few centimeters thick, made of hydrogen, helium, and heavier elements like iron, all in a plasma state where electrons are stripped from nuclei. But this atmosphere is strange because of the magnetic field. The field is so strong that atoms can't maintain their normal structure. Electrons are constrained to move in tight spirals around magnetic field lines, forming elongated, cigar-shaped orbitals rather than spherical ones. The plasma is highly polarized, meaning its properties depend strongly on direction relative to the magnetic field. Light passing through this atmosphere behaves oddly. It gets absorbed and re-emitted, scattered and polarized. The atmosphere creates spectral lines, patterns of absorption at specific wavelengths, but these lines are shifted and modified by the magnetic field. By studying these spectral features, astronomers can measure the magnetic field strength directly. Below the atmosphere is the crust, a solid layer several hundred meters thick. The crust is made primarily of iron nuclei, arranged in a crystal lattice, but it's not ordinary iron. The nuclei are packed so tightly that they form a perfect crystal, with no defects, harder than any material on Earth. The density increases with depth, and as it does, the iron nuclei become more neutron-rich, forming exotic isotopes that don't exist in nature anywhere else. The magnetic field threads through this crust, creating enormous stresses. The field wants to arrange itself in a certain way, following the laws of magnetostatics, but the solid crust resists, holding the field lines in place. Over time, the field slowly evolves, twisting and straining the crust. Eventually, the stress becomes too great, and the crust fractures in a starquake. These starquakes are not like earthquakes. They release vastly more energy, on the order of 10 to the 44 ergs or more, equivalent to a magnitude 20 earthquake, if we could scale the concept to neutron star conditions. The fracture propagates at nearly the speed of light through the crystal lattice. The magnetic field lines snap to a new configuration, releasing energy as radiation and as seismic waves that travel through the star. Beneath the crust, at depths where the density exceeds about 10 to the 14th grams per cubic centimetre, matter transitions to a different state. The iron nuclei can no longer maintain their identity. Instead, they merge into a sea of neutrons with a small fraction of protons and electrons. This is the neutron star's outer core. In this region, neutrons are packed so tightly they touch each other. Normal matter is mostly empty space, with tiny nuclei surrounded by clouds of electrons, but here there are no atoms, just neutrons pressed together. The state is called degenerate matter, and it has properties unlike anything in everyday experience. The neutrons form a superfluid, a quantum fluid with zero viscosity. If you could somehow stir a container of neutron superfluid, it would continue swirling forever, never slowing down due to friction. This superfluid can flow without resistance, passing through itself, exhibiting quantum behavior on macroscopic scales. The protons in this layer, though a minority, also form a superconductor, a state where electric current can flow without resistance. The combination of superfluid neutrons and superconducting protons affects how the magnetic field behaves. The field can penetrate the superconductor only in thin tubes called flux tubes, each carrying a quantum of magnetic flux. These flux tubes arrange themselves in a regular array, like a forest of magnetic field lines threading through the superconductor. As the star rotates and its magnetic field evolves, these flux tubes can move and rearrange, interacting with the crust, transferring angular momentum, contributing to the complex dynamics that make magnetars so active. Deeper still, at densities approaching or exceeding nuclear density, about 10 to the 15th grams per cubic centimetre, we reach the inner core. Here the physics becomes highly uncertain. The density is so extreme that we don't know for sure what state matter takes. One possibility is that neutrons break down into their constituent quarks, forming quark matter. Normally, quarks are confined inside protons and neutrons, bound together by the strong nuclear force. But at these densities, the quarks might become deconfined, forming a quark-gluon plasma, or even a strange quark matter state, where strange quarks join the usual up and down quarks. Another possibility is that exotic particles like hyperons, particles containing strange quarks, or pions, particles mediating the strong force, might appear. These particles could soften the equation of state, the relationship between pressure and density affecting the maximum mass a neutron star can have. Or perhaps something even stranger occurs. Perhaps the neutrons pair up in more complex ways, forming new superfluid phases with different symmetries. Perhaps the magnetic field creates its own exotic states of matter, states that exist only in the presence of such intense fields. The truth is, we don't know. The conditions in a magnetar's core are so extreme, the density so high, the magnetic field so strong, that our physics is incomplete. We can make educated guesses based on quantum chromodynamics, the theory of the strong nuclear force, but we can't calculate everything from first principles. There are too many unknowns, too many competing effects. What we do know is that a magnetar is a cosmic laboratory, a place where matter exists in states found nowhere else in the universe. Every observation of a magnetar teaches us something about these extreme conditions, helping us refine our theories of dense matter and strong field physics. Each magnetar is a window into realms of physics we can study in no other way. Magnetars are not quiet objects. They punctuate the cosmos with sudden, violent releases of energy that we observe as bursts and flares. Let's explore these events, understanding what causes them and what they tell us about the magnetic titans that produce them. A magnetar burst is a brief pulse of X-rays and gamma rays, typically lasting a fraction of a second to a few seconds. These bursts happen irregularly, sometimes many times per day. Sometimes with months or years between events. The energy released ranges from about 10 to the 39 ergs for a small burst to 10 to the 42 ergs for a large one. To put that in perspective, 10 to the 42 ergs is roughly equivalent to all the energy the Sun emits in a week, released in a fraction of a second. It's an enormous amount of energy, yet it's tiny compared to the total energy stored in the magnetar's magnetic field, which is about 10 to the 47 ergs. Scientists believe these bursts are caused by crustal fractures, the starquakes we mentioned earlier. The magnetic field stresses the solid crust. As the field evolves over time, trying to settle into a lower energy configuration, it builds up mechanical stress in the crust. Eventually the crust cracks, like ice fracturing on a lake or tectonic plates shifting on Earth, but vastly more violent. When the crust fractures, the magnetic field lines anchored in that region suddenly snap to a new position. This rapid rearrangement of the field accelerates charged particles to near-light speeds, creating intense beams of radiation. The energy comes from the magnetic field, converted into particle kinetic energy, and then into photons. The radiation we observe is primarily in X-rays and gamma rays, the highest energy forms of light. These photons are so energetic that each one carries thousands to millions of times more energy than visible light photons. When they hit a detector, they create a bright spike, a sudden flash that stands out dramatically against the background. Then there are the giant flares, events orders of magnitude more powerful than typical bursts. Only 3 giant flares have been observed in the modern era of gamma-ray astronomy. The first was from SGR 0526-66 in 1979, the event that first alerted astronomers to the existence of soft gamma repeaters. The second was from SGR 1900-14 in August 1998. This flare released about 10 to the 44 ergs, enough to briefly outshine the entire galaxy in gamma rays. The initial spike lasted about 1/3 of a second, followed by a pulsating tail lasting about 5 minutes, with the emission rising and falling in sync with the Magnetar's rotation. The third and most powerful was from SGR 1806-20 in December 2004, the event we mentioned earlier that affected Earth's ionosphere. This flare released about 10 to the 46 ergs, making it the brightest event ever detected from beyond our solar system. The giant flares are thought to be catastrophic crustal failures, where a large fraction of the crust fractures simultaneously, causing a massive reconfiguration of the magnetic field. The initial spike represents the moment of fracture and field rearrangement. The pulsating tail represents hot plasma trapped in the magnetosphere, the region of space dominated by the magnetic field, rotating with the star and emitting radiation as it cools. What's remarkable is that even these giant flares represent only a small fraction of the magnetic energy available. The December 2004 flare released about 10 to the -1% of the total magnetic field energy. This suggests that most of the magnetic energy dissipates gradually over thousands of years rather than in sudden dramatic events. Between bursts and flares, magnetars emit a steady glow of X-rays, powered by the decay of their magnetic fields. As the field slowly weakens over time, it releases energy that heats the star's surface. This thermal emission is less dramatic than bursts, but carries important information about the magnetar's age, temperature, and field strength. Astronomers monitor known magnetars continuously, watching for bursts and changes in behaviour. Some magnetars go through active periods, bursting frequently, followed by quiet periods with little activity. Others seem perpetually active or perpetually quiet. Understanding these patterns helps build a comprehensive picture of magnetar evolution. Each burst and flare is an event of almost inconceivable violence, yet from our perspective, safely distant. They're simply data points, photons arriving in our telescopes, telling stories of magnetic fields and crustal stresses in objects far across the galaxy. There's something peaceful in that distance, in the fact that we can study these violent processes without danger, learning from nature's extremes while remaining comfortably safe. Surrounding every magnetar is an invisible cocoon of magnetic field lines and trapped particles, a region called the magnetosphere. This is where much of the action happens, where particles are accelerated, where radiation is generated, where the magnetar's influence extends into the space around it. Let's explore this realm. The magnetosphere is the region where the magnetar's magnetic field dominates over other forces. It extends outward from the star's surface for thousands of kilometres, perhaps even further. The exact size depends on the field strength and the surrounding environment. In empty interstellar space, the magnetosphere can be quite large. If there's gas or plasma nearby, it compresses the magnetosphere, limiting its extent. The magnetic field lines form loops and arches, emerging from one magnetic pole, arcing through space and returning to the other pole. Near the star's surface, the field is so strong that it completely controls the motion of charged particles. Electrons and ions can only move along field lines, spiraling around them but unable to cross them. This creates a highly structured environment. Particles are trapped in specific regions, channeled along specific paths, their motion dictated by the magnetic geometry. It's like a three-dimensional maze where the walls are invisible but absolutely rigid, forcing particles to follow predetermined routes. As the magnetar rotates, it drags the magnetic field lines with it. Close to the star, where the field is strongest, the field lines are rigidly attached to the crust, rotating with the star as a solid body. But further out, the situation becomes more complex. The field lines want to rotate with the star, but they're also connected to charge particles that have inertia. There's a critical distance called the light cylinder, where the rotational velocity of the field lines would equal the speed of light if the rigid rotation continued. This occurs at a distance of about 48,000 kilometers for a magnetar spinning once every 10 seconds. Beyond this distance, the field lines can't maintain rigid rotation. Instead, they open up, allowing particles to escape into interstellar space. This opening of field lines creates a wind of particles and electromagnetic energy flowing away from the magnetar, similar to the solar wind from the sun but far more energetic. This magnetar wind carries away energy and angular momentum, contributing to the star's spin down. Near the magnetic poles, the field lines are open, providing escape routes for particles. Charged particles accelerated near the surface can stream outward along these open field lines, gaining energy as they go. When they emit radiation, their beams are concentrated along the magnetic axis. As the star rotates, these beams sweep across space like searchlight beams, creating the pulsed emission we observe. The magnetosphere is also where bursts and flares deposit their energy. When a starquake occurs and the magnetic field suddenly rearranges, it accelerates particles to high energies. These particles spiral along field lines, emitting synchrotron radiation, X-rays and gamma rays. They can also produce pairs of electrons and positrons through photon-photon interactions, creating a cascade of particles and radiation. In giant flares, the magnetosphere becomes a seething cauldron of activity. The magnetic field lines oscillate, creating waves that travel outward. Hot plasma is ejected from the surface, forming a cloud that rotates with the star. This plasma is so dense and hot that it radiates intensely, creating the pulsating tail observed after the initial flare spike. The plasma is confined by the magnetic field, unable to escape immediately. Instead, it cools and radiates over several minutes. Its emission modulated by the rotation as different parts of the plasma cloud come into view. Eventually the plasma cools enough and thins enough that it disperses into the magnetosphere or escapes along open field lines. The magnetosphere also interacts with the surrounding medium. If the magnetar is in a supernova remnant, the expanding shell of gas from the original explosion, the magnetosphere and the remnant influence each other. The magnetar wind can inflate a bubble in the remnant, creating a pulsar wind nebula. Conversely, the pressure from the remnant can compress the magnetosphere. Some magnetars have been found in young supernova remnants, where we can see this interaction. The remnant provides a laboratory for studying the magnetar wind and its effects. By observing the nebula's properties, the shapes and motions of the gas, astronomers can infer properties of the magnetar itself. The magnetosphere is not static. It evolves as the magnetar ages, as its magnetic field weakens, as its rotation slows. Young magnetars have more active magnetospheres, with stronger winds, more particle acceleration, more radiation. Older magnetars have quieter magnetospheres as their fields decay and their activity diminishes. Understanding the magnetosphere is crucial for interpreting Magnetar observations. The radiation we detect doesn't come directly from the star's surface in most cases. It comes from processes in the magnetosphere, from particles accelerated and radiation generated in this extended magnetic cocoon. By studying the radiation's properties, its spectrum, its pulse shape, its polarization, we can map the magnetosphere, inferring its structure and dynamics. There's a kind of beauty in this invisible architecture, these magnetic field lines threading through space, these particles following paths we can only infer, this whole complex system surrounding an object we can never visit, yet one we can study through the light it sends us across the vastness of space. One of the most important ways we study magnetars is by measuring their rotation with extraordinary precision. This technique, called timing, allows us to track how magnetars evolve, to measure their magnetic fields, and to detect subtle changes in their behaviour. Let's explore how this works. Magnetars, like all neutron stars, are cosmic clocks. They rotate with remarkable regularity, completing each revolution in a precise period that can be measured by observing their pulsed emission. Every time the magnetar rotates, a beam of X-rays sweeps across Earth, creating a pulse that arrives with clockwork precision. And magnetars do change their rotation rate. They spin down, gradually rotating more slowly as time passes. This spin down is caused primarily by magnetic braking, the process where the rotating magnetic field creates electromagnetic waves that carry away energy and angular momentum. The rate of spin down depends on the magnetic field strength. Stronger fields cause faster spin down. By measuring how quickly a magnetar is slowing down, we can calculate its magnetic field strength. This is how we know magnetars have fields of a quadrillion Gauss or more, far stronger than ordinary neutron stars. The math is relatively straightforward. The period p increases over time at a rate we call p dot, the period derivative. These two quantities, p and p dot, are related to the magnetic field strength by equations from electromagnetic theory. Given p and p dot, we can solve for b, the magnetic field. For magnetars, typical p dot values are about 10 to the negative 11 to 10 to the negative 13, meaning the period increases by that fraction each second. This might sound tiny, but over years and decades, it adds up to measurable changes. A Magnetar with a period of 10 seconds and a p dot of 10 to the negative 11 will add 1 second to its period in about 3,000 years. From p and p dot, we can also estimate the magnetar's age, at least its characteristic age, which is roughly how long it's been since it was born assuming constant spin-down rate. The formula is simple. Age equals p divided by 2 times p dot. This gives an age in seconds, which we can convert to years. For most known magnetars, characteristic ages range from a few thousand to a few tens of thousands of years. This makes them young by astronomical standards. The Sun is 4.6 billion years old. Even ordinary pulsars can be millions of years old. Magnetars are cosmic infants, still glowing with the heat of their violent births, still possessing the powerful magnetic fields they inherited from their parent stars' deaths. But timing observations reveal more than just spin down. Sometimes magnetars exhibit timing irregularities, sudden changes in their rotation that we call glitches. A glitch is an abrupt spin-up, where the rotation period suddenly decreases, meaning the magnetar starts spinning slightly faster. Glitches are thought to be caused by starquakes, the same crustal fractures that cause bursts. When the crust cracks and rearranges, it can change the star's moment of inertia, how its mass is distributed. If the change makes the mass distribution slightly more compact, conservation of angular momentum requires the rotation to speed up, like a figure skater pulling in their arms. After a glitch, the magnetar gradually spins back down, sometimes to the same rate as before, sometimes to a slightly different rate. The recovery process can take days to months, and by studying it, astronomers learn about the interior structure of the magnetar, how the superfluid interior couples to the solid crust, how angular momentum is transferred between different layers. Some magnetars also show timing noise, random fluctuations in the rotation rate that aren't predictable. This might be caused by ongoing crustal rearrangements too small to detect as individual glitches, or by changes in the magnetosphere affecting the spin-down torque, or by other processes we don't fully understand. Timing observations require patience and dedication. Astronomers use X-ray telescopes to observe magnetars regularly, recording pulse arrival times over months and years. The telescopes need to be precisely calibrated. Their clocks synchronize to atomic time standards. Any errors in timing propagate through the analysis, so careful attention to detail is essential, but the effort pays off. From timing data alone, we can measure magnetic field strength, estimate age, detect glitches, track spin evolution, and test models of neutron star structure. Combined with other observations, spectroscopy, imaging, burst monitoring, timing provides a complete picture of magnetar behavior and evolution. There's something meditative about timing work, about recording pulses night after night, watching the slow, steady march of rotation, punctuated occasionally by sudden glitches, seeing the magnetar gradually wind down over human timescales. It's a connection to deep time, to processes operating over thousands of years, yet measurable in our brief observational windows. Some of the most beautiful and informative observations of magnetars come when they're found inside supernova remnants, the expanding shells of gas created by the stellar explosions that birthed them. These systems provide a unique laboratory for studying both the magnetar and the explosion that created it. Let's explore a few examples. One of the most famous is the Magnetar at the centre of Westerlund 1, a massive young star cluster about 15,000 light-years away. The Magnetar, designated CXOJ 1647-45, was discovered in 2006, spinning once every 10.6 seconds. Its location in a young cluster allowed astronomers to estimate the cluster's age, about 3 to 5 million years, providing constraints on the progenitor star's mass. The presence of a magnetar in such a cluster is significant because it suggests magnetars can form from very massive stars, perhaps 30 solar masses or more. This has implications for supernova theory and for understanding which stellar properties lead to magnetar formation versus ordinary neutron star formation. Another remarkable system is 1E 1841-045. A supernova remnant in the constellation Aquila. At its centre is a magnetar designated SGR 1806-20, the same magnetar that produced the giant flare in December 2004. The remnant is relatively young, perhaps 10,000 years old, consistent with the magnetar's estimated age. What makes this system special is the apparent association with a massive molecular cloud nearby. Some scientists have proposed that the progenitor star formed from this cloud lived its brief life and exploded, creating the remnant and magnetar we see today. If true, this provides a complete picture of the magnetar's origins, from star formation to stellar death to neutron star creation. In all these cases, finding the magnetar in a remnant gives us information we couldn't obtain otherwise. The remnant's age provides an independent check on the magnetar's characteristic age calculated from timing. The remnant's size and expansion rate tell us about the explosion energy. The remnant's composition reveals what elements the progenitor star produced. Sometimes the interaction between magnetar and remnant creates a pulsar wind nebula, a bubble of high-energy particles and magnetic field inflated by the magnetar's wind. These nebulae glow in X-rays and sometimes in optical light, visible as a bright region surrounding the magnetar. They're powered by the magnetar's rotational energy and magnetic energy, feeding relativistic particles into the nebula, where they emit radiation through synchrotron processes. Not all magnetars are found in remnants. Some are isolated. having either been born in explosions that didn't create visible remnants, or having moved away from their birth sites, or formed from remnants that have already dispersed into the interstellar medium. These isolated magnetars are harder to age and harder to connect to their origins, but they're still valuable for studying magnetar properties. The spatial distribution of magnetars tells us something about star formation and stellar evolution in our galaxy. Most known magnetars are located in the galactic plane, the disk where most stars reside. This makes sense because magnetars are born from massive stars, and massive stars form in the dense regions of the galactic disk. A few magnetars have been found at higher galactic latitudes, away from the plane. These might have been kicked at birth by asymmetric supernova explosions, acquiring velocities of hundreds of kilometers per second. Over thousands of years, such velocities can carry them significant distances from their birthplaces. Studying magnetars in different environments, in remnants, in clusters, in isolation, in different parts of the galaxy, helps build a complete understanding of their properties and evolution. Each observation adds another piece to the puzzle, refining our models, testing our theories, revealing new aspects of these remarkable objects. And there's a poetic quality to finding a magnetar in its natal remnant, seeing the relationship between the compact, dense remnant of the core and the diffuse, expanding remnant of the envelope, both created in the same catastrophic moment. Both carrying information about that moment, both evolving according to their natures, one compressing and cooling, the other expanding and fading, two sides of the same cosmic story. Not all objects we think might be magnetars are confirmed magnetars. Some are candidates, objects with properties suggestive of magnetars but without conclusive proof. Understanding the magnetar population, how many there are, where they are, what their properties are, requires careful statistical analysis and ongoing observation. Let's explore this detective work. As of the most recent catalogues, there are about 30 confirmed magnetars, objects that have shown magnetar-like behaviour, have measured magnetic fields in the magnetar range, have been observed extensively enough to be confident of their nature. But there are also perhaps another dozen or more candidates, objects with some magnetar-like properties, but lacking definitive confirmation. A candidate might be an X-ray source with no radio pulsations, making timing difficult. Or it might be a source with a measured period and period derivative that suggest a strong magnetic field, but without observed bursts to confirm the magnetar nature. Or it might be a bursting source without a detected spin period, making field strength estimation impossible. Each candidate requires follow-up observations, sometimes over many years, to confirm or rule out the magnetar hypothesis. Sometimes a candidate suddenly bursts, providing the smoking gun evidence. Sometimes improved observations reveal a rotation period, allowing field strength calculation. Sometimes the candidate turns out to be something else entirely, an ordinary neutron star or even a different type of object. Building a complete census of the magnetar population is challenging because of selection effects and observational biases. We can only detect magnetars that are relatively nearby and relatively bright. A weak magnetar far across the galaxy might be undetectable with current instruments. A magnetar that hasn't burst recently might not stand out from other X-ray sources. Astronomers estimate that there might be 30 million neutron stars in our galaxy, based on the rate of massive star formation and evolution. If a small fraction of these are magnetars, perhaps 1% or less, there could be hundreds of thousands of magnetars in the Milky Way. But we've only detected about 30, a tiny fraction of the total. This suggests that most magnetars are either too distant to detect, too faint to observe, or currently inactive, not emitting enough radiation to be noticed. It also means that our sample of known magnetars is biased toward young, active, nearby objects, not representative of the full population. To estimate the true population, astronomers use statistical methods. They model the distribution of magnetars in the galaxy, estimate detection probabilities based on distance and brightness, and extrapolate from the known sample to the full population, these models suggest birth rates of about one magnetar per few hundred to few thousand years, meaning every few centuries or millennia. Another magnetar is born somewhere in our galaxy. Understanding the population also requires understanding magnetar lifetimes and evolution. How long does a magnetar remain active before it fades into quiescence? Current models suggest active lifetimes of 10,000 to 100,000 years, after which the magnetic field has decayed enough that the object no longer produces detectable emission. The magnetar becomes a dim, quiet neutron star, effectively invisible. But even "1 magnetars might occasionally reactivate. There's evidence that some magnetars go through cycles of activity and quiescence, perhaps related to starquakes or internal magnetic field evolution. A magnetar that's been quiet for centuries might suddenly burst again, announcing its presence anew. There's also the question of whether some radio pulsars might be old magnetars, objects whose fields have decayed to ordinary neutron star strengths, but which were once magnetars in their youth. Distinguishing these from pulsars born with normal fields is difficult, but the possibility suggests that the magnetar population might overlap with the pulsar population more than we realise. Another intriguing question is whether magnetars exist in other galaxies. A few candidates have been proposed in the Magellanic Clouds and even in more distant galaxies, but confirmation is difficult because of the large distances involved. The giant flare from SGR 0526-66, for instance, came from the Large Magellanic Cloud, 160,000 light-years away, proving that magnetars exist beyond our galaxy. In other galaxies, we might detect only the most extreme events, the giant flares bright enough to see from millions of light-years away. Regular magnetar bursts would be too faint to detect at such distances with current telescopes, but as instruments improve, we might be able to detect magnetars in nearby galaxies, expanding our sample and testing whether magnetar properties are universal or vary from galaxy to galaxy. The study of the magnetar population is an ongoing project, with new discoveries happening every few years as new telescopes come online, and existing telescopes continue monitoring the sky. Each new magnetar adds to our understanding. Each candidate provides an opportunity for detailed study. Each non-detection constrains the population properties. There's a sense of exploration in this work, of mapping a previously unknown population, of discovering how common or rare these objects are, of understanding their place in the ecology of neutron stars. It's like being a naturalist cataloguing species, except the species are magnetic titans scattered across the galaxy, each one a unique individual with its own history and properties. Magnetars are born with extraordinarily powerful magnetic fields, but these fields don't last forever. Over time, measured in thousands to millions of years, the fields decay, weakening gradually until the magnetar becomes indistinguishable from an ordinary neutron star. Understanding this decay process is crucial to understanding magnetar evolution and the fate of these objects. Let's explore how and why magnetic fields decay. The magnetic field of a magnetar stores enormous energy, about 10 to the 47th ergs for a field of 1 quadrillion Gauss. This energy has to go somewhere. It can't just disappear. Instead, it's gradually converted into other forms of energy, primarily heat and radiation, through various physical processes. One decay mechanism is ohmic dissipation, essentially electrical resistance in the neutron star's crust and core. Even though parts of the neutron star are superconducting, meaning they have zero electrical resistance, other parts are not. The normal conducting regions have some resistivity, and magnetic fields threading through these regions induce electric currents. These currents dissipate energy as heat, like current flowing through a resistor. But there's also a faster process called Hall drift. In the presence of strong magnetic fields and electric currents, the Hall effect causes the current to flow at an angle to the electric field. This creates a drift of the magnetic field, moving it around inside the star on timescales of thousands to tens of thousands of years. Hall drift doesn't dissipate energy directly, but it can reorganize the field into configurations that are easier to dissipate through ohmic processes. It can also bring the field closer to the surface, where it can more easily escape into space or interact with the magnetosphere. The interplay between Hall drift and ohmic dissipation is complex, and simulations suggest they work together to evolve the field over time. Another factor is starquakes, the crustal fractures we've discussed. Each starquake rearranges the magnetic field slightly, releasing energy and possibly accelerating the field decay. If starquakes are frequent, they might significantly contribute to field evolution. If they're rare, their effect on the overall decay might be minor. The field might also decay through ambipolar diffusion, a process where the magnetic field causes relative motion between charged and neutral particles. In the neutron star's core, there are neutrons, protons, and electrons. The magnetic field couples to the charged particles but not directly to the neutrons. This creates a drift between the charged and neutral components, which dissipates energy through collisions. Ambipolar diffusion is thought to be important in the outer core, where the density is high enough for neutrons to be a significant component, but not so high that everything is degenerate. The timescale depends on the coupling between particles and on the field strength, typically thousands to tens of thousands of years. All these processes combine to create a complex evolution. Young magnetars, just thousands of years old, have strong fields and high activity. They spin down rapidly, burst frequently, emit intense X-rays. Middle-aged magnetars, tens of thousands of years old, have somewhat weaker fields and reduced activity. Old magnetars, hundreds of thousands to millions of years old, might have fields only slightly stronger than ordinary neutron stars, with minimal bursting and faint emission. Eventually, a magnetar's field might decay to the point where it's indistinguishable from a normal neutron star. The object would still be a neutron star, still spinning, but no longer exhibiting magnetar-like behaviour. It would join the population of ordinary pulsars, or, if its spin has slowed enough, become a dim, quiet neutron star detectable only through its thermal emission. There's a possibility that field decay is not monotonic, that the field might sometimes strengthen temporarily through internal dynamo action or field reconfiguration. Some observations suggest magnetars can show variations in their spin-down rate that might reflect changes in field strength. But whether these are true field changes or just changes in how the field couples to the crust and magnetosphere is still debated. Observations support the decay scenario. There's a correlation between magnetar age, estimated from characteristic age or association with supernova remnants, and their properties. Younger magnetars tend to have stronger inferred fields, higher bursting rates, and more persistent X-ray emission. Older candidates tend to be quieter, with weaker fields and less activity. This life cycle, from violent youth to quiet old age, is a common theme in astronomy. Stars are born in violent collapses, burn brightly and fade. Galaxies form through mergers, shine intensely and quiet down. Magnetars follow a similar pattern, born in the chaos of supernova explosions, blazing with magnetic energy, gradually cooling and fading into the background population of neutron stars. Understanding magnetic field decay helps us understand the overall neutron star population. It suggests that many ordinary neutron stars might be former magnetars, that the magnetar phase is just one stage in the life of a neutron star. It also helps us predict what observations we should expect for magnetars of different ages, guiding our searches for new objects and our interpretations of known ones. Our understanding of magnetars comes not just from observations but from theoretical models and computer simulations that attempt to reproduce and explain what we see. These models are essential because we can never visit a magnetar, never probe its interior directly, never recreate its conditions in a laboratory. Let's explore how scientists model these extreme objects. The starting point is the equation of state, the relationship between pressure, density, and temperature in neutron star matter. This equation governs how the star responds to gravity, how it's structured, how it evolves. but the equation of state at nuclear densities and above is highly uncertain. We know some constraints from nuclear physics experiments and from observations of neutron star masses. The equation must support neutron stars with masses up to at least 2 solar masses, the highest precisely measured mass. It must predict radii consistent with X-ray observations. It must reproduce properties of nuclear matter at known densities. Adding a magnetic field complicates things significantly. Strong magnetic fields contribute to the pressure and energy density, affecting the structure. They also create anisotropy, meaning the star is slightly oblate, squashed along the magnetic axis. For the strongest magnetar fields, these effects can be measurable, changing the star's radius by a few %. Magnetic field configurations are modelled by solving the equations of magnetohydrodynamics, which describe how magnetic fields and fluids interact. For magnetars, these equations must account for the solid crust, the superfluid core, the superconducting regions, and the complex interplay between them. Simulations often start with an initial field configuration, perhaps a simple dipole or a more complex twisted structure, and evolve it forward in time according to the physics of field diffusion, Hall drift, and dissipation. These simulations run on supercomputers, taking weeks or months to complete, tracking the field evolution over thousands of simulated years. The results show that magnetic field evolution is complex. Fields can form stable structures or unstable ones that rapidly evolve. They can create strong toroidal components, fields wrapping around the star in circles that are hidden beneath the surface, but affect the external dipole field we observe. They can trigger starquakes when the stresses exceed the crustal strength. Another area of modelling is magnetar bursts and flares. These are simulated using magnetohydrodynamic codes that track the sudden field reconfiguration, the acceleration of particles, the emission of radiation. The simulations show that even small crustal fractures can trigger cascades of activity, with particles and radiation bouncing back and forth in the magnetosphere, amplifying the initial energy release. Giant flares are particularly challenging to model because of the extreme energies and timescales involved. The simulations must capture the fracture of the crust, happening in milliseconds, the global magnetic field reconfiguration, the ejection of plasma, and the subsequent cooling and emission over minutes. Few simulations have successfully reproduced all aspects of observed giant flares, indicating we still have more to learn. Another frontier is modelling magnetar formation in supernova explosions. This requires simulating the core collapse, the bounce, the formation of the proto-neutron star, and the development of the strong magnetic field. These simulations involve complex physics, neutrino transport, turbulent convection, magnetic field amplification, all happening in 3 dimensions over seconds of simulated time. Recent simulations suggest that strong magnetic fields can emerge from dynamo action in the proto-neutron star if the rotation is fast enough and if convection is vigorous. The field can reach magnetar strength within seconds of the bounce, but not all simulations agree on the details. And the question of what conditions produce magnetars versus ordinary neutron stars remains open. There's also the question of whether magnetar simulations can reproduce the observed population properties. If the models predict magnetar formation rates, magnetic field distributions and ages, do they match the 30 or so known magnetars? This kind of population synthesis modelling combines formation models with evolution models and observational selection effects, trying to match theory to observation. The agreement is reasonable, but not perfect. Some observed properties are well explained, others remain puzzling. For instance, why are all known magnetars relatively young? Are there old magnetars we're not detecting, or do magnetars truly have short active lifetimes? The models can explore these questions, but definitive answers require more observations. Theoretical work and simulations are iterative processes. Observations inspire new models, models make predictions, observations test those predictions, and the cycle repeats. Each iteration brings us closer to a complete understanding, though that complete understanding may always remain just beyond our grasp. There's something satisfying about watching a simulation evolve, seeing a magnetic field twist and decay over thousands of years compressed into hours of computation, seeing patterns emerge that match real observations. It's a connection between mathematics and nature, between equations on paper and objects in the sky, a reminder that the universe operates according to laws we can discover and describe, even if we can't always witness the processes directly. In recent years, a surprising connection has emerged between magnetars and another cosmic mystery: fast radio bursts. These are brief pulses of radio waves from distant galaxies, lasting only milliseconds but releasing enormous amounts of energy. The discovery that magnetars can produce fast radio bursts has opened new avenues of research and deepened our understanding of both phenomena. Let's explore this connection. Fast radio bursts, or FRBS, were first discovered in 2007 when astronomers analysing archival data from the Parkes Radio Telescope in Australia found a strange millisecond duration pulse that didn't match any known source. The burst was extraordinarily bright, and its properties suggested it came from a cosmological distance, billions of light years away. Since then, hundreds of FRBS have been detected. Most are one-off events, appearing once and never repeating. But a few are repeaters, emitting multiple bursts over time. The bursts show dispersion, a frequency-dependent delay caused by free electrons in intergalactic space. By measuring the dispersion, astronomers can estimate the distance to the source, and many FRBS appear to come from galaxies billions of light-years away. The energy released in a fast radio burst is staggering. For a burst at cosmological distance to be detectable on Earth, it must emit roughly 10 to the 39th ergs in radio waves in just milliseconds. That's comparable to the energy the Sun emits in radio waves over an entire year, compressed into a tiny fraction of a second. What could produce such an energetic, brief pulse? Many models were proposed: colliding neutron stars, evaporating black holes, exploding primordial black holes, alien civilizations. But none were entirely satisfactory. The mystery deepened. Then, in April 2020, something remarkable happened. Radio telescopes detected a bright fast radio burst from within our own galaxy, the Milky Way. This was extraordinary because previous FRBs came from distant galaxies. A galactic FRB would be much closer, allowing detailed study impossible for distant events. The source was quickly identified: SGR 1935 plus 2154, a known magnetar about 30,000 light-years away. The magnetar had just entered an active phase, emitting X-ray bursts. Simultaneously with one of these X-ray bursts, it emitted a bright radio burst with properties similar to extragalactic FRBS. The exact details are still debated. Does the emission come from the magnetar's surface, from its magnetosphere, from further out where the magnetic field opens up? Is it related to starquakes, to magnetic reconnection, to some other process? These questions are active areas of research. The Magnetar-FRB connection has several implications. First, it suggests that there might be many more magnetars than we thought, perhaps one in every large galaxy, producing FRBS that we detect as coming from great distances. This would help explain the high rate of FRBS, which is about 1,000 per day across the entire sky. Second, it provides a new way to study magnetars. FRBs carry information about the magnetar's magnetosphere, its particle acceleration processes, its magnetic field structure. By studying FRBs from known magnetars, we can learn things that are hard to learn from X-ray observations alone. Third, it raises new questions. Why do only some magnetar bursts produce radio emission? What makes a magnetar capable of producing FRBS? Are all FRBS from magnetars? Or are there multiple channels? Do young magnetars produce more FRBS than old ones? Some FRBS repeat, emitting many bursts over time. These might come from particularly active magnetars. Other FRBs are seen only once, which could mean they come from one-time events like magnetar formation, or giant flares, or simply that the magnetar hasn't burst again in the time we've been watching. The dispersion measure of FRBS, which tells us about the free electrons between us and the source, can also tell us about the magnetar's environment. Is it in a supernova remnant? Is it surrounded by a dense ionized medium? These environmental factors might affect FRB production and properties. There's also the possibility of using FRBS as cosmological probes. Since dispersion depends on the electron density along the line of sight, FRBS can tell us about the distribution of matter in the universe. If we know the distance to the FRB independently, we can measure the average electron density of the intervening space. Probing the structure of the intergalactic medium. The Magnetar FRB connection is a beautiful example of how unexpected discoveries can link seemingly unrelated phenomena. Fast radio bursts were a mystery. Magnetars were already known but poorly understood. By finding that they're connected, we've learned something new about both and opened new questions to explore. It's a reminder that the universe is interconnected. The objects and phenomena we study separately often turn out to be related in surprising ways. The Magnetar in our galaxy, bursting and flaring, might be a cousin to sources billions of light years away, all governed by the same physics, all part of the same cosmic story. Another frontier in Magnetar research is the possibility that these objects emit gravitational waves, ripples in space-time predicted by Einstein's theory of general relativity. While gravitational waves from magnetars haven't been detected yet, the search is ongoing, and a detection would open a completely new window on these mysterious objects. Let's explore this possibility. Gravitational waves are produced by accelerating masses, particularly in asymmetric configurations. Two black holes orbiting each other create strong gravitational waves that we've detected with LIGO and Virgo. Merging neutron stars do the same. But what about a single neutron star spinning by itself? The gravitational wave strain, the fractional change in distance caused by the wave, depends on the size of the asymmetry, the spin frequency, and the distance to the source. For a magnetar with a small deformation, spinning once per second, at a distance of a few thousand light years, the strain might be around 10 to the minus 26. This is incredibly small, but advanced detectors like LIGO can reach such sensitivities with long integration times. The gravitational wave frequency is twice the spin frequency, because the asymmetry passes by twice per rotation. For magnetars spinning every few seconds, the gravitational wave frequency would be fractions of a hertz to a few hertz, right in the sensitive band of ground-based detectors. Several known magnetars have been targeted in gravitational wave searches. The searches look for continuous waves, persistent signals at a known frequency that accumulates over months or years of observation. So far, no detections have been made, but the non-detections place upper limits on the magnetic deformation, constraining how much the magnetic field can distort the star's shape. These limits are already interesting. They suggest that if magnetar crusts are mountains created by magnetic stress, those mountains must be smaller than a certain size, typically fractions of a centimetre. This tells us about the crust's rigidity, its strength, how much stress it can withstand before fracturing. In the future, as detectors improve, these searches will become more sensitive. The next generation of gravitational wave observatories, like Einstein Telescope and Cosmic Explorer, will be able to detect much weaker signals. They might find continuous waves from magnetars, or from ordinary neutron stars, revealing asymmetries too small to detect now. There's also the possibility of detecting transient gravitational waves from magnetars, signals associated with starquakes or giant flares. When the crust fractures, it might produce a brief burst of gravitational waves, lasting only milliseconds, as the sudden rearrangement of mass creates ripples in space-time. These transient signals would be much harder to detect because they're brief and unpredictable. You'd need to be observing at the right time, with the detector running and sensitive. But if a nearby magnetar produces a giant flare, and if a gravitational wave detector is operating, there's a chance of detection. Detecting gravitational waves from magnetars would be revolutionary. It would give us information about the star's interior that we can't get any other way. The gravitational wave signal depends on the mass distribution inside the star, on the equation of state of ultra-dense matter. By measuring the signal precisely, we could constrain the equation of state, learning about the physics of matter at nuclear densities and beyond. We could also measure the magnetic field's effect on the star's structure directly, rather than inferring it from spin-down or spectroscopy. We could test whether the crust really does support mountains, and how large they can be. We could probe the dynamics of starquakes, seeing how the star responds to sudden internal rearrangements. Gravitational wave astronomy is still in its infancy. The first detection of gravitational waves was only in 2015. Since then, we've detected black hole mergers, neutron star mergers, and possibly other exotic events. Each detection opens new possibilities, reveals new physics, surprises us with what the universe can do. Magnetars fit naturally into this picture. They're extreme objects, likely to produce interesting signals if we look carefully enough. The search for gravitational waves from magnetars is part of the broader search for continuous waves from spinning neutron stars, one of the major goals of gravitational wave astronomy. There's a beauty in the idea that space-time itself carries information, that the fabric of reality can ripple and wave, carrying messages about distant events. Gravitational waves from a magnetar would be faint whispers in that fabric, but if we listen carefully with sensitive enough instruments, we might hear them. Learning secrets about these magnetic titans that light alone cannot reveal. Magnetars serve as natural laboratories where we can study physics under conditions that cannot be replicated on Earth. Their extreme magnetic fields, densities and energies allow us to test fundamental theories in regimes far beyond terrestrial experiments. Let's think about what we can learn from these cosmic laboratories. Quantum electrodynamics, or QED, is the theory describing how light and matter interact. It's one of the most precisely tested theories in physics, accurate to many decimal places in laboratory experiments. But those experiments operate in relatively weak fields. In magnetar fields, QED enters a completely different regime. In fields of a quadrillion Gauss, the vacuum polarization effects become significant. Virtual electron-positron pairs created from the vacuum are affected by the field, changing how light propagates. Photons can split into multiple photons. Light can be absorbed by the vacuum and re-emitted. The vacuum becomes birefringent, meaning its refractive index depends on polarization. These effects have been predicted theoretically but never tested experimentally, because we can't create such strong fields in laboratories. Magnetar observations provide the tests. By studying how light from magnetars is polarized, how spectral lines are shaped, how radiation propagates through the magnetosphere, we can test QED predictions in the strong field regime. So far, observations are consistent with QED, but the precision is limited by uncertainties in magnetar models and distances. As observations improve, these tests will become more stringent, potentially revealing new physics beyond the standard model if QED breaks down at extreme field strengths. Another area is nuclear physics. The crust of a neutron star contains exotic nuclei, isotopes with extreme neutron-to-proton ratios. These nuclei don't exist on Earth and can't be created in accelerators because they're too unstable. But in neutron star crusts, the pressure stabilizes them, allowing them to exist. The properties of these exotic nuclei affect the crust's composition, its heat capacity, its thermal conductivity, its mechanical strength. All of these influence magnetar behavior. By observing magnetar cooling, starquakes, and other phenomena, we indirectly probe nuclear physics far from the valley of stability. Magnetars also teach us about extreme plasma physics. The magnetosphere is filled with ultra-relativistic plasmas, particles moving at nearly the speed of light in magnetic fields strong enough to curve space-time. These conditions don't exist anywhere else, and studying them helps us understand astrophysical plasmas in other contexts, from pulsar wind nebulae to active galactic nuclei. The field of strong field gravity is another frontier. Magnetars have gravitational fields about 10 to the 14th times stronger than Earth's. At the surface, the gravitational redshift is about 30%, meaning light loses about 30% of its energy climbing out of the gravitational well. This is a strong field regime where general relativity is essential. By studying how light behaves near magnetars, how pulse shapes are affected by light bending, how gravitational redshift affects spectra, we test general relativity in strong fields. So far, GR passes all tests, but magnetars provide some of the most extreme tests available outside black holes. There's also the question of whether new physics might appear in such extreme conditions. Some theories predict magnetic fields can't exceed a certain strength, about 10 to the 15th Gauss, before something changes, perhaps creation of magnetic monopoles, or some phase transition in the vacuum. Magnetars approach this limit, providing tests of such exotic ideas. Similarly, theories of quantum gravity predict modifications to physics at the Planck scale, which is far beyond current reach. But magnetars might show subtle effects if quantum gravity changes how particles interact in strong fields, or if it modifies the equation of state at high densities. These effects would be tiny, but with precise enough observations they might be detectable. Magnetars are also laboratories for studying magnetic field generation and evolution. How do such strong fields form? How do they decay? What processes dominate? These questions are relevant not just for magnetars, but for understanding magnetic fields in planets, stars, galaxies, and throughout the universe. The dynamo processes that might create magnetar fields during core collapse are similar in principle to the dynamos operating in Earth's core or in the Sun's convection zone. By understanding magnetar field generation, we learn about dynamos in general, which has applications across astrophysics and geophysics. In all these ways, magnetars serve as cosmic laboratories, places where nature has created conditions we cannot, where physics operates in regimes we cannot access directly, where every observation teaches us something about the fundamental laws governing the universe. They're gifts from nature, extreme experiments set up for us to study, and all we have to do is look carefully and think deeply about what we see. Magnetars are just one type of neutron star, part of a diverse family of objects with different properties and behaviours. Understanding this diversity helps us see where magnetars fit in the larger picture and appreciate the range of outcomes possible from stellar evolution. Let's explore the Neutron Star Zoo. The most common type of observed neutron star is the radio pulsar, objects spinning rapidly and emitting beams of radio waves. There are over 2,000 known radio pulsars, far more than any other category. They have magnetic fields of about 10 to the 12th Gauss, strong but 1,000 times weaker than magnetars. They're powered primarily by their rotation, gradually spinning down as they emit electromagnetic radiation. Radio pulsars have periods ranging from milliseconds to several seconds. The millisecond pulsars are thought to be old neutron stars that have been spun up by accretion from a companion star. The slower pulsars are typically younger, not yet spun down to millisecond periods. Many pulsars are in binary systems, orbiting another star, while others are isolated. Then there are X-ray pulsars, neutron stars in binary systems that accrete matter from their companions. As material falls onto the neutron star, it's heated to millions of degrees and emits X-rays. If the neutron star has a strong magnetic field, the infalling matter is channeled onto the magnetic poles, creating hotspots that emit X-ray beams. As the star rotates, these beams create pulsations. Rotating radio transients, or RRATS, are neutron stars that emit sporadic radio pulses rather than regular pulsations. They might be ordinary pulsars whose radio beams are narrow and only occasionally sweep across Earth, or they might have some intrinsic variability. Some RRATS might be related to magnetars. Then there are the potential exotic objects like quark stars or strange stars, hypothetical neutron stars where the matter has transitioned to quark matter or strange quark matter. These haven't been confirmed, but they remain possibilities that some neutron stars might be more exotic than we think. The diversity might reflect different formation channels, different progenitor star properties, different supernova mechanisms. A massive star with strong magnetic field and rapid rotation might produce a magnetar. One with weaker field might produce an ordinary pulsar. One in a binary system might produce an X-ray pulsar after accretion starts. Or the diversity might reflect evolution. Perhaps all neutron stars go through different phases. A magnetar might start as an SGR, then become an AXP, then fade to a dim thermal emitter, then possibly reactivate as a RRAT or some other form. The life cycle could be complex, with different objects observed at different stages. There's also environmental influence. A neutron star in a supernova remnant experiences different conditions than one in isolation. One in a binary accretes matter, changing its spin and magnetic field. One moving through the interstellar medium at high speed creates a bow shock that might affect its observable properties. Understanding neutron star diversity requires understanding each type individually and then finding the connections between them. Are magnetars fundamentally different from pulsars, or are they just the high-field end of a continuum? Do all neutron stars have periods as magnetars, or only some? These are open questions. Population studies help. By cataloguing all known neutron stars and looking for correlations between age, magnetic field, spin period, environment and other properties, astronomers can identify patterns that reveal the underlying physics. Each new discovery adds to the catalogue, filling in the picture. There's something satisfying about cataloguing diversity, about seeing how many different forms a neutron star can take, how the same basic object, a city-sized ball of neutrons, can appear in so many guises depending on its history and properties. It's like studying species in biology, recognizing that underneath the diversity is a common foundation, but that the details matter enormously. Magnetars are the magnetic extremists in this family, the objects that push magnetic fields to their limits. They're rare but important, teaching us things that ordinary pulsars cannot. They're part of the broader story of neutron stars, which is itself part of the even broader story of stellar evolution, of how stars live and die and what they leave behind. There's an intriguing possibility that magnetars might be connected to gamma-ray bursts, some of the most energetic explosions in the universe. This connection is still being explored, but if confirmed, it would link magnetars to events observable across billions of light years. Let's examine this potential relationship. Gamma-ray bursts, or GRBS, are brief flashes of gamma rays from random directions in the sky, typically lasting from milliseconds to hundreds of seconds. They're divided into two classes, short GRBs, lasting less than 2 seconds, and long GRBs, lasting longer. These two classes appear to have different origins. Long GRBs are associated with supernovae, specifically the deaths of very massive stars. When a star at least 20 times the Sun's mass collapses, it can produce a gamma-ray burst if the collapse forms a rapidly rotating black hole, or magnetar, and launches jets of material at near-light speeds. These jets punch through the star's outer layers and, when they break free, produce the gamma-ray burst we observe. The connection to magnetars comes from observations and theoretical models. Some long gamma-ray bursts have X-ray afterglows that show features consistent with energy injection from a newly formed, rapidly spinning magnetar. The magnetar born in the supernova spins down rapidly, pouring energy into the surrounding material. This energy shows up as a plateau in the X-ray light curve, a period where the brightness stays relatively constant rather than fading. This plateau phase can last from hundreds to thousands of seconds, much longer than the initial burst. It suggests that something is continuously injecting energy into the system, fighting against the normal fading expected as the shockwave expands and cools. A magnetar, with its enormous rotational energy and magnetic field energy, is a plausible energy source. Some models propose that the magnetar wind, the outflow of particles and electromagnetic energy, inflates a bubble inside the supernova ejector. This bubble pushes against the outer layers, heating them and causing them to emit X-rays. As the magnetar spins down, the energy injection rate decreases, and the X-ray emission gradually fades. The timescale of the plateau depends on the magnetar's initial spin period and magnetic field strength. A magnetar spinning once per millisecond with a field of 10 to the 15th Gauss can sustain a plateau for thousands of seconds before spinning down to longer periods. The models can be fitted to observed light curves, extracting the magnetar's properties, but even in neutron star mergers, magnetars might play a role. If the merger produces a magnetar rather than immediately forming a black hole, that magnetar might survive for seconds to minutes before collapsing. During that time, it could power extended emission, a long-lasting tail of gamma rays following the initial short burst. Some short GRBs do show extended emission, and magnetar models have been proposed to explain them. The newly formed magnetar, spinning hundreds of times per second, with a field amplified by the merger, pours energy into the surrounding material. Eventually, the magnetar becomes too massive and collapses to a black hole, ending the emission. These scenarios are speculative but testable, as we observe more gamma-ray bursts with better instruments. We can look for the signatures of magnetar involvement. We can measure the energy injection, the timescales, the spectral properties, and compare them to magnetar models. There's also the possibility of observing gravitational waves from these events. A magnetar formed in a merger or collapse might emit gravitational waves if it's deformed or oscillating. Combined gravitational wave and gamma-ray observations could definitively identify magnetar formation. The connection between magnetars and gamma-ray bursts is exciting because it links phenomena observed at vastly different distance scales. Magnetars in our galaxy are relatively nearby, thousands to tens of thousands of light-years away. Gamma-ray bursts are at cosmological distances, billions of light-years away. If magnetars power some GRBs, then we're seeing similar objects in very different contexts. It also means magnetars might be more common than the local population suggests. If a significant fraction of core collapse supernovae produce magnetars, and if these magnetars power long GRBs, then there should be billions of magnetars across the universe, most too distant to detect except through their GRBs. This ties into the broader question of how common extreme events are. Are magnetars rare exceptions, or are they a natural outcome of a significant fraction of stellar deaths? Are ultra-strong magnetic fields unusual, or do they arise naturally under the right conditions? These questions touch on fundamental issues in stellar evolution and magnetohydrodynamics. The study of gamma-ray bursts continues to evolve. New satellites with better sensitivity and time resolution are being launched. Gravitational wave observatories are improving. Optical and radio telescopes are being networked to follow up GRBs quickly. Each new observation provides data to test the magnetar connection and other models. There's a beauty in the possibility that the same type of object we can study in our galactic neighbourhood might also be powering the most distant explosions we can detect, that magnetars might be both local curiosities and cosmological beacons, visible across the universe when they're young and energetic, fading into obscurity as they age but leaving their mark on the cosmic landscape. Our understanding of magnetars comes from observations across the entire electromagnetic spectrum, from radio waves to gamma rays. Each wavelength range reveals different aspects of these objects. Let's explore how astronomers observe magnetars and what each type of observation tells us. In the radio band, magnetars are generally quiet compared to ordinary pulsars. Most magnetars don't emit detectable radio pulsations. This was initially puzzling because radio emissions seem like a natural consequence of a rotating magnetic field, and magnetars have the strongest fields of all. However, a few magnetars do emit radio waves, and the discovery of the Magnetar-FRB connection has reinvigorated radio observations. When magnetars burst, they sometimes produce bright radio pulses detectable across vast distances. These radio bursts are briefer and more energetic than the steady radio emission from pulsars. Radio observations can also detect the environment around magnetars. If a magnetar is in a supernova remnant or pulsar wind nebula, those structures emit radio waves through synchrotron radiation. By mapping the radio emission, astronomers can see the magnetar's surroundings, how its wind interacts with the remnant, how energy flows from the compact object to the diffuse gas. Moving to higher energies, the infrared and optical bands are also mostly quiet for magnetars. The surface temperature of a magnetar is about 1 million Kelvin, which peaks in the X-ray range. Very little thermal emission escapes at longer wavelengths. However, if a magnetar has a surrounding nebula or disk of material, that could emit in the infrared. Some magnetars have been detected in the optical and infrared, but these detections are challenging because the objects are faint at these wavelengths and often located in crowded fields or bright nebulae. The optical emission might come from the magnetar's surface or from reprocessed X-ray emission heating surrounding material. The ultraviolet range is similarly challenging. Few observations have been made because ultraviolet astronomy requires space telescopes and because magnetars are faint in ultraviolet. But UV observations can probe the cooler outer layers of the magnetar's atmosphere, complementing X-ray observations of the hotter regions. The X-ray band is where magnetars shine brightest. Their thermal emission from the million Kelvin surface peaks in soft X-rays, around 1 to 10 kilo-electron-volts. Their bursts emit hard X-rays, 10 to 100 kilo-electron-volts and beyond. X-ray telescopes like Chandra, XMM Newton, and NuSTAR have observed magnetars extensively, providing the bulk of our data. Gamma-ray observations are crucial for understanding the most energetic magnetar processes, the star quakes and magnetic reconnection events that release enormous amounts of energy in fractions of a second. They also probe the magnetosphere's highest energy particles and most extreme acceleration mechanisms. Multi-wavelength observations combining data from radio to gamma rays provide the most complete picture. A magnetoburst might be detected simultaneously in X-rays and gamma rays, with radio follow-up searching for associated emission. The combined data constrain models much more tightly than any single wavelength. Time domain astronomy, monitoring magnetars over long periods is also essential. Magnetar behavior changes on timescales from milliseconds for bursts to years for field evolution. By monitoring continuously or regularly, astronomers can catch rare events like giant flares, track the aftermath of bursts, measure long-term trends in luminosity and spin-down, and detect transitions between active and quiescent states. The development of automated alert systems has been crucial. When a magnetar bursts, satellites detect it immediately and send alerts to ground-based telescopes, which can quickly observe the source to catch the afterglow or search for associated emission. This rapid response has led to many important discoveries. Space-based observatories are essential for magnetar studies because Earth's atmosphere blocks X-rays and gamma rays. Chandra, XMM Newton, Swift, Fermi and other missions have dedicated significant time to observing magnetars. Future missions like Athena and Strobe-X will provide even better sensitivity and time resolution. Ground-based telescopes contribute through optical and infrared follow-up and through radio observations. The combination of space and ground capabilities across the spectrum gives us the comprehensive view needed to understand these complex objects. Each wavelength is like a different sense, revealing aspects invisible to the others. Radio tells us about FRBS in the environment. Optical and infrared show us surrounding nebulae and companions. X-rays reveal the hot surface and bursting activity. Gamma rays probe the most extreme energy releases. Together, they paint a full portrait. There's something satisfying about this multi-wavelength approach, about using every available tool to study a distant object, piecing together a coherent picture from photons of all energies, spanning 12 orders of magnitude in frequency, all originating from a city-sized sphere thousands of light-years away. The study of magnetars is far from complete. Many questions remain unanswered, and new discoveries continue to surprise us. Let's think about where magnetar research is heading, what new observations and theories might teach us in the coming years and decades. One major frontier is discovering more magnetars. With only 30 confirmed objects, our sample is small. Finding more magnetars, especially in different environments or with different properties, would greatly improve our statistical understanding. Future X-ray missions with wider fields of view and better sensitivity will discover fainter, more distant magnetars. There's particular interest in finding magnetars in different evolutionary stages. We have young magnetars, a few thousand years old. We have middle-aged candidates. But we don't have confirmed old magnetars, objects hundreds of thousands of years old with significantly decayed fields. Finding such objects would test evolutionary models directly. Another frontier is precision measurements. Current magnetic field estimates have uncertainties of factors of a few. Improved spectroscopy, measuring absorption lines with higher resolution, could determine field strengths more precisely. This would test models of how fields decay and evolve. Timing precision is also improving. With longer baselines of observation and better X-ray timing instruments, we can measure spin evolution more accurately, detect smaller glitches, and probe the star's interior structure through timing noise and glitch recovery. Gravitational wave observations remain a major goal. A detection of continuous waves from a magnetar would revolutionize the field, providing direct measurement of asymmetry and constraining the equation of state. Even non-detections are valuable, setting limits that inform models. The Magnetar FRB connection will continue to be explored. Are all FRBs from magnetars? What fraction of magnetars produce detectable FRBs? Can we use FRB rates to estimate the total magnetar population, including objects too distant or faint to detect otherwise? These questions will drive radio observations in coming years. Theoretical work will advance as computers become more powerful. Simulations of magnetar formation, field evolution, and bursting activity will include more physics, higher resolution, and longer timescales. These simulations will make testable predictions that observations can verify or refute. The equation of state of ultra-dense matter is another priority. Neutron star observations, including magnetars, are one of the best ways to constrain this. Combined with gravitational wave observations of mergers, laboratory measurements of nuclear properties, and theoretical calculations from quantum chromodynamics, we're converging on a more complete understanding. Another frontier is magnetars in other galaxies. We've detected a few magnetar giant flares from the Magellanic Clouds. Could we detect them from more distant galaxies? Improving gamma-ray detectors might make this possible, opening a window on extragalactic magnetars and allowing population studies beyond our Milky Way. There's also interdisciplinary work connecting magnetophysics to other areas. The extreme conditions in magnetars are relevant to nuclear physics, plasma physics, solid-state physics, and fundamental physics. Insights from magnetar studies could inform work in these fields, and vice versa. Educational outreach is another aspect. Magnetars capture the public imagination with their extreme properties. They're natural hooks for teaching about physics, astronomy, stellar evolution, and the scientific method. Communicating magnetar science to broader audiences helps inspire the next generation of scientists. International collaboration will be crucial. Magnetar research involves scientists from many countries using telescopes and satellites operated by different agencies, sharing data, coordinating observations, and working together across borders maximizes the scientific return. As we look to the future, there's a sense of excitement about what we'll discover. Each new Magnetar teaches us something. Each burst reveals new physics. Each theoretical advance deepens our understanding. The field is alive, active, full of puzzles to solve and phenomena to explain. There's also humility in recognizing how much we still don't know. We've learned a tremendous amount in the decades since Magnetars were proposed, but fundamental questions remain. How do the strongest magnetic fields form? How do they evolve? What triggers giant flares? What's the connection to other neutron star classes? What role do magnetars play in the broader universe? These questions will occupy astronomers for decades to come. And that's a good thing. Science is most exciting when there are mysteries to solve, when the answers aren't known yet, when each observation might reveal something new. Magnetars provide that excitement in abundance. As we near the end of our journey through the realm of Magnetars, let's pause and reflect on what these objects represent, not just as astrophysical phenomena, but as expressions of nature's capacity for extremes, as reminders of how strange and wonderful the universe can be. Magnetars exist at the edge of what's physically possible. Their magnetic fields approach the theoretical maximum beyond which vacuum instabilities might occur. Their densities are so extreme that atoms cannot exist, only exotic states of matter found nowhere else. Their energies, released in bursts and flares, exceed anything we encounter in everyday life by factors of billions or trillions. Yet despite these extremes, magnetars obey the same physical laws that govern everything else. The equations of general relativity, quantum mechanics, electromagnetism, nuclear physics all apply. The same mathematics that describes a falling apple or an electric circuit describes the behaviour of magnetars. The universe is unified in its laws, even as it's diverse in its phenomena. There's something profound in that unity. The fact that we can understand magnetars at all, that we can write equations describing their properties, that we can make predictions tested by observations, shows that human reason can grasp even the most extreme manifestations of nature. Our minds, evolved to hunt and gather on African plains, can comprehend objects whose magnetic fields would tear us apart from thousands of kilometers away. This is both humbling and empowering. Humbling because it shows how tiny we are, how local our experience, how limited our direct sensory knowledge of the cosmos. But empowering because it shows that despite these limitations, we can extend our understanding through thought, mathematics, and careful observation. We're not limited to what we can touch or see with our eyes. This beauty extends to the observations. X-ray images of magnetar environments, showing glowing nebulae and shock waves. Light curves showing the pulsations as the star rotates. Spectra with absorption lines distorted by intense magnetic fields. Each is a window into physics operating under extreme conditions, and each has an aesthetic quality beyond its scientific content. Magnetars also connect us to deep time and to the grand cycle of stellar evolution. The matter in a magnetar was once in a massive star, fusing hydrogen in its core. Before that, it was in a molecular cloud, perhaps created in earlier generations of stars. After the magnetar fades, its matter will continue to drift through space, perhaps eventually forming new stars or planets. We're part of this cycle too. The atoms in our bodies were created in stars, some in the cores of massive stars like magnetar progenitors, some in supernovae. We're literally made of stardust, connected through matter and time to the same processes that create magnetars. This cosmic perspective can be either overwhelming or comforting, depending on how you look at it. Overwhelming because it shows how insignificant any individual life is in the vast scheme of cosmic evolution. Comforting because it shows we're part of something larger, that our existence connects to the deepest processes in nature, that we're not separate from the cosmos but integral to it. Studying Magnetars is, in a sense, studying ourselves, understanding the universe that created us, the laws that govern both the largest and smallest scales, the processes that transform simple elements into the complex structures capable of thought and wonder. There's also wisdom in accepting the limits of our knowledge. We don't fully understand magnetars. We have good models, strong evidence, testable predictions, but mysteries remain. The exact formation mechanism, the detailed field evolution, the trigger for giant flares, all are areas of active research where we don't have complete answers. This incomplete knowledge is not a failure, but an opportunity. It's what drives scientific progress, what motivates new observations and theories, what keeps the field exciting. If we knew everything about magnetars, they would be less interesting. The mystery is part of the appeal. And perhaps there's a lesson here for life more broadly. Not everything needs to be fully understood to be appreciated. Mystery, uncertainty, and the unknown can coexist with knowledge and wonder. We can study magnetars rigorously while still feeling awe at their existence. We can be scientific and poetic simultaneously. As we enter these final chapters, let's shift from the detailed science to something more contemplative. Thinking about magnetic fields not just as physical phenomena, but as invisible architectures that shape the cosmos, as forces that connect distant objects, as structures both rigid and fluid, both simple and infinitely complex. Magnetic fields are, in a sense, invisible lines of force threading through space. We can't see them directly, can't touch them, can't perceive them with our ordinary senses. Yet they're real as the matter they influence. They carry energy, exert forces, shape the behaviour of charged particles and plasma across the universe. On Earth, we experience magnetic fields in small ways. A compass needle aligning with Earth's field, a magnet holding a note to a refrigerator. These are gentle interactions, almost negligible in the scale of forces we encounter daily. Yet even Earth's weak field extends thousands of kilometres into space, protecting us from solar radiation, creating the aurora in polar skies. The Sun's magnetic field is stronger, reaching hundreds of Gaussian sunspots, organising the solar atmosphere into loops and arches visible in images. These field lines emerge from the Sun's surface, arc through the corona, and return, creating structured pathways that plasma follows. When the field reconnects, it releases energy in solar flares, bright flashes and eruptions that dwarf anything on Earth. Moving further, pulsars have fields of 1 trillion Gauss, dominating their environments, creating magnetospheres where particles spiral along field lines at near-light speeds, emitting beams of radiation visible across the galaxy. These fields are rigid enough to channel particle beams, strong enough to affect the neutron star's structure, and then magnetars, with fields 1,000 times stronger still, where the magnetic force becomes one of the dominant influences on the star itself. The field stores more energy than the star's rotational energy, more than its thermal energy. The field can stress and fracture the solid crust. The field shapes the space-time around the star. In a broader sense, magnetic fields connect objects across vast distances. The galactic magnetic field, though weak, permeates the Milky Way, organising interstellar gas, influencing star formation, deflecting cosmic rays. This field connects every star, every neutron star, every black hole in the galaxy through invisible lines of force. The fields themselves have a kind of life, evolving and changing over time. They're generated by moving charges, by rotating plasma, by currents flowing through conductors. Once generated, they persist, diffusing and decaying according to the laws of electromagnetism. They can amplify through dynamo action, growing stronger as energy is pumped into them. In magnetars, the field evolution is a slow dance spanning millennia. The field tries to relax to lower energy configurations, but the solid crust resists, maintaining stresses. Eventually, The crust yields in a starquake, and the field snaps to a new configuration. This cycle repeats, the field gradually weakening, the star slowly releasing its magnetic energy. There's beauty in the mathematics of magnetic fields, described by Maxwell's equations, 4 elegant expressions that capture everything about how electric and magnetic fields behave. These equations predict electromagnetic waves, explain light, unify electricity and magnetism into electromagnetism, and apply from the smallest scales to the largest. The same equations that describe a radio antenna on Earth describe the magnetosphere of a magnetar. The same principles that let us generate electricity in power plants operate in the dynamos of stars and planets. The unity of physics, the fact that the same laws apply everywhere, is both profound and beautiful. Magnetic field lines are often visualized as curves in space, flowing from north to south poles, never crossing, filling space with structure. This visualization, though simplified, captures something real. The field does have direction and magnitude at every point. Particles do follow these lines. The structure is meaningful. In a magnetar's magnetosphere, the field lines form complex loops and arches, some closed, returning to the star, others open, extending to infinity. This geometry determines where particles can go, where radiation is emitted, how energy flows from the star to the surroundings. The invisible architecture shapes everything. And there's wonder in thinking about how this architecture emerged from the collapse of a stellar core, how the simple magnetic field of the original star was amplified a billionfold in a fraction of a second, how the laws of physics inevitably created this extreme configuration once certain conditions were met. It's as if the universe has a palette of possibilities, and magnetars are what happens when nature paints with the brightest colours, the strongest forces. The most extreme configurations. They're not subtle, they're bold, dramatic, intense, and they exist not because they're useful or serve a purpose, but because the laws of physics allow them, because they can. This raises a kind of existential question. Why does the universe contain such extremes? Why isn't everything moderate, comfortable, familiar? The answer, perhaps, is that the laws of physics don't care about our comfort. They permit a range of outcomes, and nature explores that full range, creating everything from the gentle to the violent, from the mundane to the exotic. Magnetars are reminders that the universe is vast in its possibilities, that extremes exist because they can, that wonder lies not just in the familiar but in the edge cases, the rare objects, the phenomena that push against the limits of what's possible. They're cosmic exclamation points, declaring that nature is more creative, more powerful, more strange than our daily experience suggests. Let's think for a moment about the human side of magnetar science, about the people who discover these objects, who develop theories, who spend nights at telescopes, who dedicate careers to understanding these distant magnetic titans. Because science is not just about facts and equations, it's also about curiosity, persistence, and the very human drive to understand. The story begins with theoretical predictions. In the 1930s, physicists like Walter Baird and Fritz Zwicky proposed that neutron stars might exist, formed in supernova explosions. This was pure theory, mathematical speculation about what might happen under extreme conditions. They had no observations, no evidence. Just the logic of physics suggesting that such objects could be real. For decades, neutron stars remained theoretical curiosities. Then in 1967, Jocelyn Bell Burnell discovered pulsars, proving that neutron stars exist and opening a new field of astronomy. Bell was a graduate student, working long hours analysing radio data by hand, looking for scintillation signals from quasars instead. She found something completely unexpected. The discovery could easily have been missed. The regular pulses looked artificial at first, like interference or a problem with the equipment. It took careful checking, patience, and scientific rigour to confirm they were real astronomical signals. Bell's discovery changed astronomy, but it also shows how progress depends on attention to detail, on not dismissing the unexpected. Over the following decades, observations confirmed the Magnetar model. Chrysakou Veliotou and her team measured the spin-down of SGR 1806-20, proving its magnetic field was extraordinary. Victoria Caspi and her collaborators studied Magnetar timing extensively, discovering glitches and tracking evolution. Each observation was another piece of the puzzle, another confirmation of the model. These scientists spent years, even careers, on Magnetar research. They wrote proposals to get telescope time, analysed data, wrote papers, attended conferences, debated interpretations. They experienced the frustrations of unclear data, failed observations, rejected papers. They also experienced the joys of discovery, the excitement of seeing a prediction confirmed, the satisfaction of understanding something new. Science is often portrayed as a series of breakthroughs, but the reality is mostly slow, careful work. Most observations don't reveal dramatic new phenomena. Most theories turn out to be wrong or incomplete. Progress comes through accumulation, through many small steps rather than giant leaps. But those small steps matter. Each new magnetar discovered adds to the sample. Each well-measured magnetic field constrains models. Each detected glitch provides information about neutron star interiors, collectively. These efforts build a coherent picture of what magnetars are and how they work. There's also collaboration. Magnetar research involves astronomers, physicists, theorists, observers, people with different expertise working together. Someone might discover a new magnetar. Someone else measures its spectrum. A theorist models the observations. A computer scientist develops analysis software. Everyone contributes. And there's international cooperation. Telescopes and satellites are operated by agencies around the world. Data is shared openly. Scientists from different countries work together on projects. The Magnetar catalogue is a product of global effort, built by people who might never meet in person but who share a common goal. The human story also includes mistakes and dead ends. Proposed magnetars that turned out to be something else. Theories that didn't pan out. Observations that were later found to be incorrect. Science isn't a straight path to truth but a winding journey with many detours. But mistakes are part of the process. They teach us what doesn't work, refining our understanding, and they're reminders of humility, that we don't have all the answers, that nature is complex and sometimes surprising, that we should hold our ideas lightly, ready to revise them when new evidence appears. There's also the next generation of scientists, students and postdocs who are continuing the work. They're building on what came before, asking new questions, developing new techniques, finding new magnetars. They'll make the discoveries that weren't possible in earlier decades, using better instruments and drawing on accumulated knowledge. This continuity, the passing of knowledge and passion from one generation to the next, is how science progresses. Each generation builds on the previous one's work, pushing the boundaries a little further, understanding a little more deeply, discovering new phenomena to puzzle over and explain. And underlying all of this is curiosity, the very human trait of wanting to understand, to know, to explore. Why do magnetars exist? What makes their field so strong? How do they evolve? These aren't questions with practical applications for daily life. Nobody needs to understand magnetars to grow food or build houses or cure diseases. But we ask anyway, because we're curious, because understanding the universe is intrinsically valuable, because knowledge for its own sake matters. This is one of the most beautiful aspects of being human, the capacity to wonder about things beyond our immediate needs, to seek truth for its own sake. Magnetar research, like all pure science, is a celebration of this capacity. It's people choosing to spend their lives studying distant objects that will never affect them directly. Motivated by curiosity and the joy of discovery, it's a profoundly human endeavour, as uniquely human as art or music or philosophy. As we move through these final chapters, Let's think about the space between magnetars, the vast voids where these objects do not exist, the quiet regions of the galaxy where only ordinary matter floats, where nothing extreme happens, where the universe is gentle and still. For every magnetar in the galaxy, there are millions of cubic light-years of empty space. Space is mostly empty, mostly quiet, mostly dark. The drama of magnetar bursts, the intensity of their magnetic fields, the violence of their formation, these are rare punctuation marks in a universe that's mostly peaceful silence. In the regions between stars, the density is almost nothing. A few atoms per cubic centimetre, mostly hydrogen with traces of helium and heavier elements. This is 10 trillion times less dense than air. It's as close to perfect vacuum as anything in nature, yet it's not truly empty. Those few atoms matter. They're the raw material for future stars and planets. There's something peaceful about imagining this vast quiet space. No sounds, because there's no medium for sound to travel through. No wind, no weather, no change except the slow drift of gas clouds and the gradual expansion of the universe. Just stillness, darkness, and the patient flow of time. Occasionally something happens. A star explodes, sending a shock wave through the gas, compressing it, heating it, triggering new star formation. Or a pulsar beam sweeps by, invisible to the eye but detectable with radio telescopes. Or cosmic rays, high-energy particles accelerated somewhere, pass through on their journeys across the galaxy. But these are rare events in any given volume of space. Most of the time, most of the space, nothing happens. The atoms drift, the photons pass, time flows. This quiet space is not wasted or meaningless. It's essential. Without it, galaxies would be too crowded, gravitational interactions too frequent, stability impossible. The emptiness allows structures to form and persist, allows light to travel cleanly, allows the universe to be observable and comprehensible. It also provides perspective on the magnetars we've been discussing. They're extraordinary, yes, but they're also small and localized. A magnetar's influence extends at most a few thousand kilometers through its magnetosphere, perhaps further through its wind, but beyond that, space returns to its usual quiet state. The radiation from a magnetar spreads outward at the speed of light, diluting as it goes, until at great distances it's just a faint signal, barely distinguishable from background. To an observer in another galaxy, even a giant magnetar flare would be just a brief blip, gone in seconds, swallowed by the vastness. This doesn't diminish magnetars, it contextualizes them. They're part of a larger whole, remarkable objects in a universe that's mostly unremarkable, islands of extremity in an ocean of calm. There's wisdom in appreciating both the extraordinary and the ordinary, both the dramatic and the quiet. Magnetars teach us about extreme physics, but the quiet space teaches us about patience, stillness, the beauty of emptiness. In meditation traditions, there's value in emptiness, in the space between thoughts, in silence. The universe, in its own way, is mostly meditation, mostly quiet, with occasional moments of activity. Perhaps we can learn from this cosmic rhythm, finding peace in stillness while still appreciating the moments of intensity. As we contemplate magnetars, spinning alone in the darkness, separated from each other by thousands of light years, we can also contemplate the darkness itself. The void that surrounds them, the quiet space where nothing happens but where everything that does happen has room to unfold. This space is not nothing. It's filled with potential, with possibility, with the fundamental fields and quantum fluctuations that underlie reality. It's where light travels, where gravity propagates, where the universe breathes between its moments of creation and destruction. And it's where we, from our small planet, look out and wonder, sending our telescopes' light-gathering eyes into the darkness, searching for the rare bright spots where something extraordinary is happening, while also appreciating the vast quiet between. We've learned so much about Magnetars in this journey together. But let's be honest about what we still don't know, about the mysteries that remain, and about the value of living comfortably with uncertainty, with questions that have no current answers, perhaps no answers at all. We don't know exactly how magnetars form. We have good models, reasonable scenarios involving rapidly rotating proto-neutron stars with vigorous dynamos, but the details are uncertain. We can't observe core collapse directly. We can't see inside a forming neutron star. We have to infer from theory and from observations of the end products. We don't know why some neutron stars become magnetars while others don't. Is it the progenitor star's mass, its rotation, its magnetic field? Is it the details of the collapse, the geometry, the initial conditions? Is it random chance, quantum uncertainty in the collapse process? We have hypotheses, but no definitive answer. We don't know the precise equation of state of ultra-dense matter. We know it must support at least 2 solar masses, must predict reasonable radii, but within those constraints, many equations of state are possible, until we measure neutron star properties precisely enough to distinguish between them, or until we have better theoretical understanding from quantum chromodynamics. The equation of state remains uncertain. We don't know if there are types of magnetars we haven't discovered yet. Perhaps there are ultra-high field magnetars with even stronger fields, or low-field magnetars transitional between ordinary pulsars and magnetars, or magnetars in exotic environments we haven't explored. Our sample is small and possibly biased towards certain types. We don't know for certain that all fast radio bursts come from magnetars, or if only some do, or what fraction of magnetars produce detectable FRBs. We have one clear example from our galaxy, but generalizing from one case to the entire population is uncertain. These uncertainties are not failures, they're opportunities. They're the questions that will drive research in coming years. They're what makes the field exciting, dynamic, alive. If we knew everything, there would be nothing left to discover. And there's a kind of peace that comes with accepting uncertainty. We don't have to have all the answers to appreciate magnetars. We can marvel at what we do know while remaining humble about what we don't. We can be confident in our models while staying open to revision. This balance between knowledge and ignorance is central to the scientific attitude. We make claims based on evidence, but we hold those claims provisionally, ready to update when better evidence appears. We're confident but not dogmatic, informed but not closed-minded. Contrast this with other ways of knowing that claim absolute certainty. Religious dogma, political ideology, philosophical systems that claim to have final answers. Science is different. It's built on uncertainty, on the willingness to say quote 2 or quote 3 or quote 4. This epistemic humility is not weakness but strength. It allows science to progress, to correct itself, to improve over time. Theories that seemed certain 100 years ago have been replaced or refined. What we think we know now about magnetars will likely be similarly refined or replaced by future discoveries, and that's okay. That's how it should be. We're learning gradually, patiently, building understanding piece by piece. We don't need final answers. The journey of discovery is the point, not the destination. Living with mystery also means being comfortable with the limits of human understanding. Our brains are finite, our lifetimes brief, our perspective limited. We can't know everything, can't understand every detail, can't resolve every paradox. And that's fine. The universe is under no obligation to make sense to us. It exists according to its own laws, indifferent to whether we understand. The fact that we understand as much as we do, that we can make sense of magnetars at all, is remarkable. We should celebrate that understanding while accepting its limits. There's also beauty and mystery in the unknown. A universe completely understood might be less interesting than one with deep questions remaining. The mystery invites exploration, wonder, contemplation. It gives us something to think about, to be curious about, to spend our lives investigating if we choose. So as we think about magnetars, let's hold both knowledge and ignorance, both what we've learned and what we still wonder about. Let's be grateful for the insights while being excited about the mysteries. Let's appreciate that we live in a time when we know Magnetars exist, when we can study them, when we can ask meaningful questions about them, even if we don't yet have all the answers. This is the human condition, knowing enough to wonder, wondering enough to seek, seeking enough to learn, learning enough to realize how much more there is to know. It's a cycle that never ends. And in that endless cycle is both the frustration and the joy of being conscious, curious beings in a vast, strange, wonderful universe. In these final moments of our journey, let's think about time itself, about the eternal rotation of Magnetars, about the slow but inexorable passage of eons, and about our own brief moment of awareness in the vast cosmic story. A Magnetar spins, once every few seconds, completing rotation after rotation, each one slightly slower than the last. In the time we've been together tonight, the nearest Magnetar has completed perhaps 1,000 rotations. 1,000 sweeps of its radiation beam across the cosmos, 1,000 pulses that travelled through space at light speed. These rotations have been happening for thousands of years, since the Magnetar was born in its supernova explosion. Before humans had written language, before civilization, before agriculture, this Magnetar was spinning. It spun through the rise and fall of empires, through ice ages and warm periods, through mass extinctions and the evolution of new species. It will continue spinning long after we're gone. In 1,000 years, 10,000, 100,000, the Magnetar will still be there, still rotating, though more slowly, its magnetic field weaker, its emission fainter. Eventually, perhaps 1,000,000 years from now, it will have slowed and cooled enough to become invisible to our instruments, fading into the population of quiet neutron stars. But it won't stop. Conservation of angular momentum ensures it keeps spinning, perhaps forever, though so slowly that the rotation period might be measured in minutes or hours rather than seconds. Unless some external event disrupts it, a collision with another object or infall into a black hole, it will continue its slow rotation for eons beyond our ability to comprehend. There's something meditative about this eternal spin, this patient rotation in the darkness of space. No purpose, no goal, just the simple following of physical law, the momentum imparted during the star's collapse continuing indefinitely. We, in contrast, are brief. Human lives last perhaps 100 years. Our civilizations have existed for thousands, our species for hundreds of thousands. Even the sun, our source of life and energy, will last only billions of years before exhausting its fuel. Everything we know, everything we are, is temporary. The Magnetar outlasts us all, indifferent to our existence, spinning alone in the dark, yet we're the ones who know it's there, who have named it, measured it, tried to understand it. In our brief moment of consciousness, we've reached out across thousands of light years to study an object that will exist long after we're gone. This is both humbling and remarkable. Humbling because it shows our cosmic insignificance, our tiny role in the vast universe. Remarkable because despite that insignificance, we can understand, can think, can wonder. Consciousness, brief as it is perhaps the universe's way of knowing itself. When we observe a Magnetar, we're participating in a kind of cosmic self-awareness. The atoms that make up the Magnetar and the atoms that make up us were created in similar processes, in stellar cores and supernova explosions. We're both star stuff, to use Carl Sagan's phrase, and through our observations, through our telescopes and equations, the universe examines part of itself. From this perspective, the Magnetar's entire history, from its formation to its distant future when it fades into darkness, exists as a world line in space-time, a four-dimensional structure that simply is, timelessly. Our own lives are similar world lines, shorter, intersecting briefly with the present moment of Earth's history. These world lines don't intersect directly. We'll never visit a Magnetar, never see one up close. But they connect through light, through the photons that leave the Magnetar's surface, travel across space, and arrive at our telescopes. In those photons is information, a message from the Magnetar to us, a connection across the void. And through our thoughts, through our understanding, we connect back. The photons bring information about the Magnetar. Our minds process that information, building models, developing theories, understanding. In this exchange, separated by distance but connected by light and thought, we and the Magnetar are in relationship. This relationship will end when we do, when human civilization ends, when consciousness in our form ceases to exist. But perhaps other intelligences on other worlds will observe the same Magnetar, will see its radiation and wonder, will build their own theories and models. The Magnetar will outlast us, but not outlast all observers. Or perhaps it will. Perhaps consciousness is rare. Perhaps we're alone or nearly so. Perhaps when we're gone, the Magnetar will spin in darkness, observed by no one, known by no one, understood by no one. Does it matter if there's no one to observe? Perhaps not. The Magnetar spins regardless. Physical law operates regardless. The universe exists regardless of observers. But something is lost when consciousness ends. The only witness to the cosmos, the only way the universe knows itself, gone. These thoughts can lead to melancholy or to appreciation. We exist now, briefly, able to see and think and wonder. Rather than mourning the eventual end, we can celebrate the temporary gift of consciousness, the chance to be aware, to learn, to understand, to connect with distant objects through light and thought. The Magnetar spins in eternal present, following its nature. We exist in our own eternal present, following ours. Both are part of the cosmic dance, the eternal interplay of matter and energy, structure and chaos, existence and void. And in this dance, brief as our part is, we find meaning, beauty, and wonder. Thank you for staying with me through this long exploration of Magnetars, the universe's most powerful magnets. We've spent 2.5 hours together, journeying from the formation of these cosmic titans to their eventual fade into darkness, from the physics of extreme magnetic fields to the quiet space between stars. I'm grateful you chose to spend this time contemplating these remarkable objects. We've travelled together through many ideas. We explored what Magnetars are, how they're born in the violent deaths of massive stars, how their extreme magnetic fields affect everything about them. We learned about starquakes and giant flares, about spin down and timing, about magnetospheres and radiation. We discovered connections to fast radio bursts and gamma-ray bursts, to gravitational waves and fundamental physics. We also thought about the human side, the scientists who discovered and study these objects, the limits of our knowledge, the mysteries that remain. We reflected on extremes and the ordinary, on time and consciousness, on our brief moment of awareness in the vast cosmic story. And now, as we reach the end, let's return to the simple fact of Magnetars themselves. They exist. Right now, scattered through our galaxy, about 30 confirmed Magnetars are spinning in the darkness, their magnetic fields thousands of times stronger than ordinary neutron stars, their surfaces hot and glowing, their crusts occasionally fracturing in starquakes that release more energy than the sun emits in years. The answer to the question, what are magnetars, is simpler than all the physics we've discussed. They're neutron stars with extraordinarily strong magnetic fields. But the deeper answer, the one we've spent hours exploring, includes all the complexity, the physics, the observations, the mysteries, the connections to broader astrophysics. Probably, based on what we know, Magnetars are born when massive stars collapse and certain conditions are met, rapid rotation perhaps, strong initial fields, vigorous dynamos. But we're not certain. The exact formation mechanism remains an area of active research. If you enjoyed this slow drift through extreme physics and cosmic wonders, a like and subscribe helps others find these calm explorations. And if you have thoughts about Magnetars, about what we've discussed, or questions about these objects, the comments are a space for sharing. To those already part of this community, thank you for being here, for bringing your curiosity to these explorations. Wherever you are in the world right now, I hope you found some peace in this journey. I hope your breathing has slowed, that the concerns of the day have faded to background, that your thoughts have turned to the cosmos and the remarkable objects it contains. I hope your mind feels calmer, your body more relaxed, ready for rest. Look up at the stars if you can see them from where you are, or imagine them if you can't. Somewhere among those points of light too faint and distant to see are magnetars. Spinning alone in the darkness, their magnetic fields invisible but powerful, their surfaces hot and glowing in X-rays, occasionally bursting with energy that travels across the galaxy. All those magnetars came from stars, massive giants that lived brief, brilliant lives before exploding. The explosion scattered elements into space, enriching the cosmos, creating the raw materials for new stars, new planets, perhaps new life. The cores collapsed into magnetars, carrying forward a small part of the original star's mass and angular momentum, compressed into city-sized spheres of neutrons. The mystery of why some cores become magnetars while others become ordinary neutron stars remains. Perhaps it's the rotation, perhaps the magnetic field of the progenitor star, perhaps something else we haven't thought of yet. The universe keeps its secrets, revealing them slowly, requiring patience and careful observation. But here we are nonetheless, aware of these objects, able to study them from our safe distance, learning about physics in regimes we can never create in laboratories, testing our theories against nature's most extreme experiments. That's a gift. The fact that the universe creates such objects and places them where we can observe them. Sleep well tonight. Dream of stars collapsing and neutron stars forming, of magnetic fields so strong they warp reality itself, of cosmic lighthouses spinning in the darkness, of bursts and flares releasing the energy of 1,000 suns in a fraction of a second. Dream of the quiet space between stars, vast and dark and patient. Dream of the scientists who spend careers studying these objects, who write proposals and analyze data, and develop theories and slowly, piece by piece, build understanding. Dream of future discoveries, new magnetars found, mysteries solved, surprises revealed. Dream of the eternal spin, magnetars rotating for thousands, millions, billions of years, following physical law, indifferent to observation, yet knowable, understandable, part of the cosmic story we're all embedded in. And rest in the knowledge that the universe is vast and strange and wonderful, that it contains objects like magnetars alongside objects like us, that consciousness exists to wonder about existence. That in our brief moment we can reach across space and time to understand distant phenomena. Good night. Rest peacefully. Let your thoughts drift like photons through space, carrying information, connecting distant objects, participating in the cosmic dance. The magnetars will keep spinning, the universe will keep evolving, and when you wake, you'll be part of it still. Conscious matter in a cosmos that permits consciousness. Sleep well. Dream of magnetic titans. Good night.